Scientists point their telescopes to the sky, trying to see beyond our human reach, only to find the improbable, a system like no other. 7 Earth-sized worlds, all tightly packed, circling a small, cool star. Some of these planets are nestled in a zone where water, crucial for life as we know it, could exist as a liquid. In 2017, the discovery of Trappist-1 filled headlines around the world, igniting a new wave of excitement. This star system, so compact and unique, offered a glimpse into possibilities previously only dreamed of. What truly lies there? Could these worlds harbour life, perhaps even intelligent beings, watching us right now from billions of miles away? Before we begin, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below, subscribe to our channel, and settle in for a fascinating journey. In the vast, silent canvas of the cosmos, countless stars twinkle, each a distant sun, a potential hearth for worlds unknown. Our own sun, a brilliant yellow beacon, dominates our sky and nurtures life on Earth. But it represents just one type of star. Among the staggering number of luminous spheres scattered across the universe, a particular kind of star reigns supreme in its sheer abundance, the Red Dwarf. These are not the fiery giants that capture immediate attention, nor the pulsing beacons that astronomers often chase. Instead, they are the quiet, unassuming, yet incredibly numerous stars that dot our galaxy, fading into the background of a truly grand celestial tapestry. One such star, seemingly unremarkable at first glance, has captured the imagination of scientists and dreamers alike: Trappist-1. This humble red dwarf, cooler and smaller than our Sun, holds within its gravitational embrace a system of 7 planets, some of which exist in a zone where the conditions for liquid water and perhaps life might just align. To understand the profound implications of Trappist-1, we must first understand the nature of its faint red sun. A red dwarf star is, at its heart, a stellar minimalist. These are the smallest and coolest type of stars on what astronomers call the main sequence, a stage where stars spend the majority of their lives by fusing hydrogen into helium in their cores. Unlike the Sun, which is a medium-sized yellow dwarf, red dwarfs possess significantly less mass. Their mass typically ranges from about 7.5% of our Sun's mass to around half of its mass. This fundamental difference in mass is the key to understanding all of their other unique characteristics. Less mass means less gravitational pressure in their cores. With less pressure, the temperatures and densities within a red dwarf's core are also much lower than those found in larger stars. Consequently, the nuclear fusion reactions that power these celestial furnaces proceed at a vastly slower, more subdued pace. This sluggish rate of hydrogen consumption is what gives red dwarfs their characteristic dimness and their extraordinary longevity. To put its size into perspective, imagine our Sun as a large, bright orange. Trappist-1, by comparison, would be no bigger than a grapefruit, perhaps even smaller, resembling a large plum. More precisely, Trappist-1 has a radius that is only about 11.7% of the Sun's radius. This makes it only slightly larger than the planet Jupiter, the largest gas giant in our own solar system. While Jupiter is a planet and not a star, this comparison helps to visualize just how small a star Trappist-1 truly is. Its mass, as mentioned, is also considerably less, roughly 9% of the Sun's mass. This means it has less material pulling inward, resulting in its compact size. This miniature stature directly impacts its luminosity. The Sun blazes with an average luminosity of 1 solar unit. Trappist-1, on the other hand, emits only about 0.05% of the Sun's total light. This makes it incredibly faint, almost too dim to be seen with the naked eye even if it were closer, a true testament to its faint nature as a red dwarf. The temperature of a star is directly related to its mass and the rate of its nuclear reactions. Because red dwarfs have less mass and slower fusion rates, they are significantly cooler than our Sun. Our Sun's surface temperature hovers around 5,778 Kelvin, giving it its characteristic yellow-white hue. Trappist-1, in stark contrast, has a surface temperature of approximately 2550 Kelvin. This much lower temperature explains its red designation. Stars, like hot coals, glow with different colours depending on their temperature. The hottest stars appear blue or white, while cooler stars emit light primarily in the red and infrared parts of the electromagnetic spectrum. This means that if you were to stand on a planet orbiting Trappist-1, the light from its star would appear much redder than our sunlight, and a significant portion of its energy would be invisible to human eyes, existing as infrared radiation or heat. This dominance of infrared light has profound implications for any life that might exist on its orbiting planets, as their biology would need to adapt to a different energy spectrum for processes like photosynthesis. The prevalence of red dwarfs across the galaxy is truly astounding. They are by far the most common type of star in the universe. Estimates suggest that red dwarfs make up between 70% to 85% of all stars in the Milky Way galaxy. For every star like our Sun, there are several, if not many, red dwarfs quietly burning. This numerical dominance is a direct consequence of star formation processes. When vast clouds of gas and dust collapse under their own gravity to form new stars, it appears that the universe has a strong preference for creating smaller, less massive stars. It takes less material and less extreme conditions to ignite a red dwarf compared to a massive blue giant, or even a medium-sized star like our Sun. This means that statistically, if life is to emerge and thrive around stars, it is far more likely to do so around a red dwarf simply because there are so many of them. This abundance makes systems like Trappist-1 not just scientific curiosities, but crucial targets in the broader search for life beyond Earth. If life is common, it is most probable to be found orbiting these humble, faint red suns. Perhaps the most compelling characteristic of red dwarfs, from the perspective of potential life, is their extraordinary lifespan. While our Sun is expected to live for approximately 10 billion years before swelling into a red giant and eventually fading into a white dwarf, red dwarfs like Trappist-1 are veritable stellar Methuselahs. Because they consume their hydrogen fuel at such a remarkably slow rate, they are predicted to live for trillions of years. This is not a typo, trillions of years. Some estimates suggest the smallest red dwarfs could shine for as long as 10 trillion years, far outstripping the current age of the universe, which is roughly 13.8 billion years. This incredible longevity stems from a unique internal process. Unlike larger stars that burn hydrogen primarily in their cores and gradually accumulate helium, red dwarfs are fully convective. This means that the material within the star is constantly circulating, effectively mixing the entire star's hydrogen fuel from the core to the surface and back again. This continuous stirring prevents helium ash from building up in the core, allowing the star to burn nearly all of its hydrogen, not just the hydrogen in its central region. This efficient, slow burn is the secret to their virtually endless existence. The implications of this immense lifespan for the potential evolution of life are profound. On Earth, life took billions of years to evolve from single-celled organisms to complex intelligent beings. Our Sun has provided a stable environment for approximately 4.5 billion years, and life has flourished for much of that time. If a red dwarf star can provide a stable energy source for trillions of years, it offers an almost unimaginable amount of time for life to emerge, adapt, and evolve. Planets around red dwarfs could theoretically host life for far longer periods than planets orbiting stars like our Sun. This extended period could allow for multiple evolutionary pathways, the development of highly complex ecosystems, or even the rise and fall of countless civilizations over cosmic timescales. It suggests that if life is a natural outcome of planetary formation and suitable conditions, then red dwarfs, despite their dimness, might be the true cradles of enduring cosmic biology. However, this extraordinary longevity does not come without its challenges for the habitability of orbiting planets. Red dwarfs, particularly in their youth, can be surprisingly active, prone to powerful flares and bursts of high-energy radiation. While their overall light output is dim, these stellar tantrums can be many times more powerful than flares from our Sun, potentially stripping away planetary atmospheres or delivering lethal doses of radiation to any nascent life. A planet would need a robust magnetic field, similar to Earth's, to shield it from these energetic onslaughts. Furthermore, because red dwarfs are so faint, any planet hoping to harbour liquid water must orbit incredibly close to the star to receive enough warmth. This close proximity often leads to a phenomenon known as tidal locking, where the planet's rotation slows until one side perpetually faces the star while the other side is locked in eternal night. This creates extreme temperature differences across the planet, with a scorching hot day side and a frozen night side, potentially leaving only a narrow temperate band in between where life could survive. However, even these challenges are subjects of intense scientific debate and research, with new models suggesting that thick atmospheres or ocean currents could help to redistribute heat, making a tidally locked world more hospitable than previously thought. The faint red sun, Trappist-1, with its long, slow burn, presents a cosmic paradox, a seemingly humble star that offers an immense stretch of time for life to flourish, yet demands significant adaptations from any worlds that call it home. Its gentle glow promises stability for eons, a silent witness to the long, slow dance of evolution. To truly appreciate the significance of the Trappist-1 system, we must first understand its position within the grand, sweeping cosmic structures that make up our universe. It is not enough to simply say it is far away. Its location within the vastness of the Milky Way galaxy, our galactic home, and its distance from our own solar system provide crucial context for why this particular system has become such a focal point for astronomical study. Our universe is a tapestry of galaxies, each containing billions or even trillions of stars, gas, dust, and mysterious dark matter, all held together by gravity. The Milky Way is just one thread in this cosmic fabric, albeit a magnificent one, and Trappist-1 is a tiny, albeit incredibly significant knot on that thread. The Milky Way is a majestic barred spiral galaxy, a colossal pinwheel of stars, gas, and dust spanning approximately 100,000 light-years across. It is characterized by a central bar-shaped structure composed of stars, from which spiral arms gracefully unfurl. Our Sun, along with its retinue of planets, including Earth, resides in one of these spiral arms, specifically the Orion arm, sometimes also referred to as the local arm. We are situated about 27,000 light-years from the galactic centre, where a supermassive black hole named Sagittarius A star lurks. From our vantage point within the Orion arm, we are about halfway out from the core to the edge of the galactic disk. Our solar system, along with billions of other stars, slowly orbits the galactic centre, completing one full revolution roughly every 230 million years. This journey through the galaxy is a stately, unhurried waltz through cosmic time. Now let us turn our attention to Trappist-1. This fascinating system is also a resident of the Milky Way galaxy, just like our own Sun. More precisely, Trappist-1 is located within the same general galactic neighbourhood as our solar system, residing within the galactic disk and likely within one of the Milky Way's spiral arms. It is not in the dense, chaotic galactic core, nor is it in the sparse, ancient halo that surrounds the main disk. Its placement in the disk means it is part of the dynamic star-forming regions of our galaxy, surrounded by other stars, gas clouds, and dust that characterize these active areas. The fact that it is within our galactic disk makes it, in cosmic terms, a relatively accessible target for observation compared to systems located in distant galaxies or even in the far reaches of our own galaxy's less populated regions. When we talk about the distance to Trappist-1, astronomers use a unit called the light year. A light year is not a measure of time, but a measure of distance. It is the distance that light travels in one Earth year. Light travels at an incredible speed, approximately 186,000 miles per second, or nearly 300,000 kilometers per second. So, a light year represents a truly immense distance. Trappist-1 is located approximately 39 light-years from Earth. To put this into perspective, if you could travel at the speed of light, it would still take you 39 years to reach the Trappist-1 system. Our fastest spacecraft, like the Voyager probes, are travelling at speeds vastly slower than light. If Voyager 1 were heading towards Trappist-1, it would take many tens of thousands of years to cover the same distance. The number 39 might sound small, but when it refers to light years, it describes a truly staggering cosmic gulf. This distance, while immense by human standards, is considered relatively nearby in the grand scale of the universe. For astronomical observation, nearby is a relative term. The closer a star system is, still lies in the sheer vastness of space. Its faintness means that our instruments must be incredibly sensitive, capable of detecting minute changes in light from a distant dim star. Observing the tiny, almost imperceptible dips in its light as its planets pass in front of it requires exquisite precision and long hours of observation. Furthermore, resolving individual planets or studying their atmospheres requires technologies at the very edge of our current capabilities, such as those found on the James Webb Space Telescope. The light from Trappist-1 that reaches us today began its journey 39 years ago, a silent messenger from the past carrying information about that distant star and its planets. However, this very distance also fuels the excitement. The fact that we can detect such a complex system, with multiple Earth-sized planets, at this range is incredibly promising for the future of exoplanet research. It means that our current technology is powerful enough to find and study systems that are not just theoretical but tangibly present in our cosmic backyard. Every new observation, every new piece of data gleaned from the faint light of Trappist-1 pushes the boundaries of our understanding of planetary formation and the potential for life beyond our solar system. The excitement comes from the possibility that we're on the cusp of truly answering one of humanity's oldest questions. Are we alone in the universe? Trappist-1, due to its comparative closeness, offers one of the best chances to begin answering that question in a truly scientific and observational manner. It is a stepping stone, a proof of concept, that allows us to refine our techniques and develop new ones for studying even more distant worlds. Beyond individual stars and their planetary systems, the universe is structured in a hierarchy of neighbourhoods. These range from the immediate stellar environment to vast clusters of galaxies. Our solar system is part of a stellar neighbourhood that includes a few dozen other stars within about 15 light-years. These stars are gravitationally bound, though loosely, or are simply passing through our immediate vicinity. We are also part of a larger stellar association, a group of stars that likely formed from the same giant molecular cloud and are moving together through space. The Milky Way itself is part of a larger structure called the Local Group, a collection of over 50 galaxies, most of which are small dwarf galaxies, gravitationally bound together. The two largest members of the Local Group are our Milky Way and the Andromeda Galaxy, which is about 2.5 million light-years away, and is on a collision course with our galaxy, a cosmic dance that will unfold billions of years from now. The Triangulum Galaxy is the third largest. The Local Group in turn is part of an even larger supercluster of galaxies known as the Virgo supercluster. This immense structure, roughly 110 million light-years across, contains thousands of galaxies and is slowly drawing them towards its gravitational centre, a region known as the Virgo cluster. On even larger scales, superclusters are not randomly scattered, but form filamentary structures, enormous walls and sheets of galaxies, separated by vast cosmic voids where very few galaxies are found. This intricate network of filaments and voids is often referred to as the cosmic web, the largest known structure in the universe, believed to have formed from the gravitational collapse of primeval density fluctuations in the early universe. Trappist-1, along with our solar system, exists within this grand cosmic hierarchy. It is a star within a spiral arm of the Milky Way, part of the Local Group of galaxies, which itself is embedded within the Virgo supercluster, all threads in the vast cosmic web. Its immediate stellar neighbourhood is characterized by a density of stars similar to our own, neither exceptionally crowded nor unusually sparse. This means that Trappist-1 is surrounded by other stars that could potentially host their own planets, forming a dynamic environment of stellar systems. Understanding Trappist-1's place in space not only helps us pinpoint it for observation, but also helps us to understand the typical environments in which stars and planets form and evolve. Its presence in our galactic disk, a region teeming with star formation and relatively stable for billions of years, reinforces the idea that planetary systems are not isolated oddities but rather a common feature of our galaxy. The continued study of Trappist-1 promises to unlock secrets not just about this single, fascinating system, but about our own humble place in the awe-inspiring, silent and endless cosmic ocean. The search for planets beyond our own solar system, known as exoplanets, has revolutionized our understanding of the universe. For centuries, the idea of other worlds orbiting distant suns was relegated to the realm of science fiction and philosophical speculation. It was a beautiful thought, but one without concrete evidence. This began to change dramatically in the late 1980s and early 1990s, when astronomers developed innovative techniques to detect these elusive celestial bodies. The initial discoveries were of giant planets, often many times the size of Jupiter, orbiting incredibly close to their stars. These were not the Earth-like worlds that many hoped to find, but they proved that planets outside our solar system were real and abundant. This opened the floodgates for a new era of astronomical exploration, leading to thousands of confirmed exoplanets and an ever-growing understanding of the diversity of planetary systems. Among these countless discoveries, one system in particular has ignited immense excitement and captivated the world: Trappist-1. Its story is a testament to scientific ingenuity, dedicated observation, and a relentless pursuit of knowledge. The journey to finding Trappist-1 began with a specific kind of telescope and a clever strategy. Located at the La Silla Observatory in Chile, high in the dry Atacama Desert, is a robotic telescope named TRAPPIST. The name TRAPPIST is an acronym standing for Transiting Planets and Planetesimal Small Telescope. It is a relatively modest instrument, with a mirror just less than 2.5 feet, or 75 centimeters, in diameter. However, its small size belies its power and importance. TRAPPIST was designed with a very specific mission in mind: to search for planets transiting or passing in front of very small and cool stars known as ultra-cool dwarf stars, or more commonly red dwarfs. These stars are much smaller and fainter than our Sun, and this characteristic makes them ideal targets for the transit method of planet detection. The logic behind focusing on red dwarfs is straightforward. When a planet passes in front of its star, it blocks a tiny amount of the star's light. The bigger the planet is in relation to its star, the more light it blocks, and the larger the dip in brightness that astronomers can observe. For a star like our Sun, which is quite large, an Earth-sized planet blocks only a minuscule fraction of its light, making the detection incredibly challenging. But for a red dwarf, which can be just barely larger than the planet Jupiter, an Earth-sized planet blocks a much larger percentage of the star's light, creating a much more noticeable dip. This makes the signal from a transiting planet around a red dwarf much easier to detect with existing technology. TRAPPIST was specifically built to capitalize on this advantage, continuously monitoring dozens of these faint red suns, patiently waiting for the telltale signs of a planetary transit. Among the many stars on TRAPPIST's watch list was a dim, nondescript star known in earlier catalogues as 2MASS J2 3062928 -0502285. This rather cumbersome name was later simplified to TRAPPIST-1, reflecting the telescope that made the crucial observations. TRAPPIST-1 had been identified as an ultra-cool dwarf star, a perfect candidate for TRAPPIST's mission. The telescope began its meticulous monitoring of TRAPPIST-1 in September 2013. For months it collected data, patiently recording the star's brightness over long stretches of time. The data was then analysed by a team of astronomers led by Michael Gillen from the University of Liège in Belgium. They were looking for this subtle, periodic dimming that would indicate a planet passing in front of the star. The first hint of something extraordinary came in late 2015. The TRAPPIST data revealed clear, repeating dips in the brightness of TRAPPIST-1. These dips were consistent with the presence of not just one, but 3 distinct planets orbiting the star. The dips were remarkably deep for such small planets, confirming the advantage of targeting a red dwarf. The initial findings suggested 3 planets, roughly Earth-sized, tightly orbiting their faint red sun. The discovery was immensely exciting, a strong signal that this particular red dwarf system was special. However, astronomical discoveries of this magnitude always require rigorous confirmation. A single telescope's observations, no matter how convincing, are rarely enough to declare a definitive planetary system. The scientific method demands independent verification, and further data to build an undeniable case. To confirm their initial findings and to search for additional planets, the team needed more powerful instruments and more eyes on Trappist-1. This led to a large-scale international collaborative effort. They enlisted the help of other ground-based telescopes, including the Speculus survey, which stands for Search for Habitable Planets Eclipsing Ultra-Cool Stars. Speculus is a network of robotic telescopes specifically designed to follow up on interesting targets identified by Trappist and similar surveys. These telescopes, also located in Chile, provided crucial additional data, allowing astronomers to observe Trappist-1 for longer periods and with higher precision. They could confirm the transits of the initially detected planets, making sure they were not simply random fluctuations or instrumental errors. But the real game-changer in confirming the Trappist-1 system came with the involvement of a space-based observatory, the Spitzer Space Telescope. Spitzer, operated by NASA, is an infrared telescope, meaning it observes the universe in infrared light, which is essentially heat radiation. This capability made it uniquely suited to studying Trappist-1. Red dwarfs emit most of their light in the infrared part of the spectrum. Therefore, Spitzer could observe Trappist-1 and its transiting planets with much greater clarity and sensitivity than optical telescopes that see invisible light. Furthermore, being in space, Spitzer was free from the distortions of Earth's atmosphere, which can blur observations and make it harder to detect faint signals. Most importantly, Spitzer could provide continuous, uninterrupted observations of Trappist-1 for weeks on end. Ground-based telescopes are limited by daylight and weather, but Spitzer could stare at the star day and night, patiently gathering data. The Spitzer Space Telescope began its intensive observation campaign of Trappist-1 in late 2016. Over a 20-day period, Spitzer continuously monitored the star, collecting an unprecedented amount of data. This continuous vigil proved incredibly fruitful. The exquisite precision of Spitzer's infrared observations not only confirmed the existence of the three initially detected planets, Trappist-1b, C, and D, but also revealed 4 more. These new discoveries were Trappist-1e, F, G, and H, bringing the total number of known planets in the system to an astounding 7. The Spitzer data was so detailed that it allowed astronomers to not only confirm the planets, but also to begin characterizing them, estimating their sizes and their orbital periods with remarkable accuracy. The light curves from Spitzer were a treasure trove of information, showing a complex dance of multiple planets transiting their star, each leaving its unique signature on the star's light. The discovery of 7 Earth-sized planets, with several potentially residing in the star's habitable zone, was an almost unbelievable outcome. The habitable zone is the region around a star where temperatures are just right for liquid water to exist on a planet's surface, a key ingredient for life as we know it. While the initial Trappist observations were exciting, the Spitzer follow-up truly cemented the extraordinary nature of the Trappist-1 system. It revealed a dynamically packed system, with all 7 planets orbiting incredibly close to their star and to each other. Their orbits are so close that from the surface of one planet, the other planets would appear as large, distinct disks in the sky, sometimes much larger than our own moon appears from Earth. This close proximity also leads to strong gravitational interactions between the planets, causing subtle variations in their transit times, known as transit timing variations, or TTVs. These TTVs became an additional powerful tool for confirming the planets, and even allowed astronomers to estimate their masses, providing crucial information about their densities. The culmination of these years of observation, analysis, and collaboration came in February 2017. NASA held a major press conference to announce the full findings of the Trappist-1 system. The announcement sent shockwaves through the scientific community and captivated the public worldwide. News outlets globally reported on the discovery of the 7 Earth-sized planets and the tantalizing possibility of life beyond our solar system. The sheer number of planets, their Earth-like sizes, and the fact that 3 of them were seemingly located within the habitable zone made Trappist-1 an instant celebrity in the exoplanet world. It was a discovery that resonated deeply, not just with scientists, but with anyone who has ever looked up at the night sky and wondered if we are truly alone. Since that landmark announcement, Trappist-1 has remained one of the most intensely studied exoplanet systems. astronomers continue to observe it with a variety of instruments, both from the ground and from space. The launch of the James Webb Space Telescope in late 2021 marked a new era for Trappist-1 research. Webb, with its unparalleled infrared sensitivity and advanced spectrographic capabilities, is uniquely positioned to peer through the atmospheres of the Trappist-1 planets. By observing how the star's light passes through their atmospheres during transits, Webb can detect the presence of different gases, potentially including water vapour, carbon dioxide, and even biosignatures like oxygen or methane, which could hint at the presence of life. The story of finding Trappist-1 is not just about a single discovery. It is an ongoing saga of scientific exploration, a testament to humanity's persistent drive to understand our place in the universe and to find answers to the profound questions that the cosmos continually poses. The faint red sun continues to be watched, its secrets slowly being unveiled, one tiny dip in brightness at a time. The discovery of exoplanets, worlds orbiting stars other than our Sun, has been one of the most exciting frontiers in astronomy over the past 3 decades. Before the 1990s, the existence of such planets was purely theoretical. Now, thanks to ingenious observational techniques, we know that exoplanets are not rare exceptions, but rather a common feature of our galaxy. Among the various methods astronomers use to find these distant worlds, one stands out for its effectiveness and the wealth of information it provides: the transit method. It is a technique that relies on a simple, yet powerful principle of celestial mechanics, and it has been instrumental in the discovery and characterization of thousands of exoplanets, including the fascinating worlds of the Trappist-1 system. At its core, the transit method is about observing light. Imagine a distant star shining steadily. If a planet happens to pass directly in front of that star from our viewpoint on Earth, it will block a tiny fraction of the star's light. This causes a momentary slight dip in the star's apparent brightness. This phenomenon is called a transit, much like how Venus or Mercury can occasionally transit, or pass in front of, our Sun as seen from Earth. The key here is the alignment. For us to observe a transit, the planet's orbital plane must be almost perfectly edge-on with respect to our line of sight. If the orbit is tilted too much, the planet will simply pass above or below the star, and we would never see it block any light. This requirement means that the transit method can only find a small fraction of all exoplanets out there, but for those that are aligned just right, it offers a treasure trove of information. To detect these minuscule changes in brightness, astronomers use highly sensitive telescopes and instruments called photometers. A photometer measures the intensity of light coming from a star over time. The data collected by a photometer is then plotted on a graph called a light curve. A light curve shows how the brightness of a star changes over a period. For a star with no transiting planets, the light curve would ideally be a flat line, indicating constant brightness. However, when a planet transits, the light curve exhibits a very specific characteristic pattern. It will show a sudden, sharp decrease in brightness as the planet begins to cross the face of the star, followed by a period of sustained lower brightness as the planet is fully in front of the star, and then a return to the original brightness as the planet moves off the star's disk. This creates a distinctive U or V shape in the light curve. The beauty of the transit method lies in what we can learn from these light curve dips. First and foremost, the depth of the dip provides crucial information about the planet's size. A larger planet will block more of the star's light than a smaller one. Imagine a tiny pebble crossing a light bulb versus a small ball crossing the same bulb. The ball will cause a noticeably larger shadow. So by measuring how much the star's light dims, astronomers can calculate the planet's radius relative to the star's radius. For example, if a star's light drops by 1%, it means the planet covers 1% of the star's surface area. Knowing the star's size, which can often be estimated from its temperature and brightness, allows astronomers to then determine the absolute size of the planet. This is how scientists determined that the planets in the Trappist-1 system are roughly Earth-sized. Secondly, the duration of the dip tells us about the planet's orbital characteristics. The length of time the planet takes to cross the face of the star can give clues about its orbital speed and how far away it is from its star. Planets closer to their stars orbit faster and complete their transits more quickly than planets farther away. This duration, combined with the time between successive dips, leads to the third crucial piece of information, the planet's orbital period. If a planet transits every 5 days, then its orbital period, its year, is 5 Earth days long. By observing multiple transits over an extended period, astronomers can precisely pin down these orbital periods, which in turn allows them to calculate the average distance of the planet from its star using fundamental laws of physics, such as Kepler's laws. The transit method is particularly powerful for systems like Trappist-1, which harbour multiple transiting planets. When there are several planets in a system, their individual transits create a more complex light curve. The dips might overlap, or occur very close together, making it challenging to disentangle each planet's signature. However, this complexity also offers a unique opportunity to learn even more. The gravitational pull between closely orbiting planets can subtly alter their orbital paths, causing their transit times to vary slightly from what would be perfectly regular. This phenomenon is known as transit timing variations, or TTVs. If a planet is sometimes pulled forward in its orbit by a neighbouring planet, its transit might occur a few minutes or even hours earlier than predicted. Conversely, if it is pulled backward, its transit might be delayed. By meticulously tracking these tiny deviations in transit times, astronomers can infer the presence of other planets in the system, even those that might not transit. More importantly, TTVs can be used to estimate the mass of the transiting planets. The amount of gravitational pull a planet exerts depends on its mass. So, by measuring how much a transiting planet's orbital period is perturbed by its neighbours, scientists can calculate its mass. Combining this mass information with the radius information derived from the transit depth allows astronomers to determine the planet's average density. Density is a critical property because it tells us something about the planet's composition. A high density suggests a rocky, Earth-like composition, while a low density points to a gas-rich or icy composition. For the Trappist-1 planets, the analysis of TTVs was absolutely crucial in confirming the 7 planets and determining their masses, ultimately showing that they are indeed predominantly rocky worlds, much like Earth. While incredibly powerful, the transit method does have its limitations. As mentioned, the most significant limitation is the need for a precise orbital alignment. Only a small percentage of planetary systems will be oriented in such a way that we can observe transits from Earth. This means that for every transiting planet we find, there are likely many more non-transiting planets that remain hidden from this method. Another challenge is the issue of false positives. Sometimes, other astronomical phenomena can mimic a planetary transit. For example, a background binary star system, where 2 stars orbit each other and one occasionally eclipses the other, can produce a similar dip in light. Or a star with a large dark star spot rotating into view might also cause a dimming. Astronomers employ various techniques and follow-up observations to rule out these false positives, often combining transit data with other methods, such as the radial velocity method, which detects the wobble of a star caused by the gravitational pull of an orbiting planet. The transit method is also particularly effective when applied to smaller, dimmer stars, like the Red Dwarfs. As discussed in the previous chapter, a planet of a given size blocks a larger fraction of light from a small star than from a large star. This makes the signal from a transiting planet around a red dwarf much stronger and easier to detect. This is precisely why the Trappist telescope was designed to observe these kinds of stars, and why the Trappist-1 system, with its 7 Earth-sized planets orbiting an ultra-cool dwarf, has provided such rich data for astronomers. The strong signal allowed for the precise measurements that led to the discovery of all 7 worlds and the subsequent characterization of their sizes and masses. Beyond simply detecting planets and determining their basic properties, the transit method opens up even more advanced avenues of research, particularly concerning planetary atmospheres. When a planet transits its star, a tiny fraction of the star's light passes through the planet's atmosphere before reaching our telescopes. Different gases in the atmosphere absorb specific wavelengths of light. By carefully measuring the small changes in the star's spectrum during a transit, astronomers can identify the chemical composition of the planet's atmosphere. This technique is called transmission spectroscopy. It is an incredibly challenging observation, requiring extremely sensitive instruments and long observation times, especially for Earth-sized planets around small stars. However, it is one of the most promising ways to search for biosignatures, which are gases like oxygen or methane that could indicate the presence of life on another world. The James Webb Space Telescope, with its powerful infrared capabilities, is specifically designed to perform these kinds of sophisticated, atmospheric analyses on planets like those in the Trappist-1 system. The magic of the transit method lies in its simplicity, its elegance, and its incredible power. From tiny dips in starlight, astronomers can deduce the size, orbital period, and even the mass and density of distant worlds. It allows us to peek into systems billions of miles away, transforming abstract points of light into real, tangible planets, each with its own unique characteristics. The discovery of the Trappist-1 system, with its harmonious ballet of 7 Earth-sized worlds, stands as a crowning achievement of the transit method. It exemplifies how patiently observing the universe, waiting for the precise alignment of celestial bodies, can unlock profound secrets and bring us closer to answering the age-old question of whether we are alone in the vast cosmic ocean. The transit method continues to be a cornerstone of exoplanet research, constantly pushing the boundaries of what we can learn about worlds far, far away. The discovery of a planetary system beyond our own is always a cause for scientific excitement, but the unveiling of Trappist-1 was truly exceptional. It was not just 1 or 2 new worlds, it was a cosmic revelation of 7 distinct planets, all roughly the size of Earth, circling a dim red star. This tightly packed arrangement, a miniature solar system nestled close to its parent star, immediately captured the imagination of astronomers and the public alike. It presented a unique opportunity to study a planetary system where multiple potentially habitable worlds exist, offering an unprecedented laboratory for understanding planetary evolution and the conditions necessary for life. The very existence of these 7 sister worlds, as they have sometimes been called, challenges our preconceived notions of what a planetary system can be and how it can be configured. What makes the Trappist-1 system so remarkably unique is not just the number of planets, but their uniformity in size and their incredible proximity to their star and to each other. All 7 planets are comparable in size to Earth. Planet B, the innermost, is about 85% the radius of Earth, while Planet F, one of the middle worlds, is about 103% the radius of Earth. This consistent terrestrial scale is a stark contrast to many other exoplanet discoveries, which often involve gas giants much larger than Jupiter, or super-Earths that are 2 or 3 times the size of our home world. The fact that astronomers found 7 planets, all within this specific size range, around a single small star, was a stunning outcome of their diligent observations. This collection of similarly sized, rocky worlds immediately raised questions about their formation and evolution, suggesting a common origin or a shared history within the system. The most striking feature of the Trappist-1 system is its astonishing compactness. If our solar system were to shrink to the scale of Trappist-1, all of its planets, from Mercury to Neptune, would fit comfortably inside the orbit of our innermost planet, Mercury. In the Trappist-1 system, the entire family of 7 planets could orbit closer to their star than Mercury orbits our Sun. The outermost planet, Trappist-1H, completes an orbit in about 18.7 Earth days. Compare this to Mercury, which takes 88 Earth days to orbit the Sun. This means that even the furthest planet in the Trappist-1 system orbits its star in less than a quarter of the time it takes Mercury to orbit ours. The planets are incredibly close to their star, a necessity for them to receive enough warmth from the faint red dwarf to potentially support liquid water. This extreme closeness to the star also means the planets are remarkably close to each other. From the surface of one planet, another planet might appear as a prominent feature in the sky, sometimes looking many times larger than our moon appears from Earth. Imagine looking up and seeing a large, distinct sphere of another world, perhaps with discernible land masses, clouds, or even glints of light reflecting off vast oceans. This cosmic ballet of neighbouring worlds would create a constantly changing celestial panorama, a sight far more dynamic than anything experienced on Earth. This visual spectacle underscores the tightly knit nature of this planetary family, where gravitational interactions and shared skies are a daily reality. The proximity of the planets also leads to strong gravitational interactions between them. Their orbits are not perfectly regular. Instead, they are locked in a rhythmic, resonant dance. For example, for every 2 times planet B orbits Trappist-1, planet C orbits 3 times. For every 2 orbits of planet C, planet D completes 3. This precise, synchronized motion, known as an orbital resonance, means that the planets exert regular, predictable gravitational tugs on each other. These gravitational nudges, though subtle, are incredibly important for scientists. By observing the tiny variations in the timing of their transits, how early or late a planet crosses in front of its star, astronomers can precisely measure the masses of each planet. This allows them to calculate the density of each world, providing crucial clues about their internal composition. For the Trappist-1 system, these transit timing variations confirmed that the planets are predominantly rocky, with densities comparable to Earth's, suggesting they are not gas giants or icy worlds but solid bodies. Several of the Trappist-1 planets reside within what astronomers call the habitable zone. The habitable zone, sometimes referred to as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on a planet's surface. Not too hot, where water would evaporate into space, and not too cold, where it would perpetually freeze. Because Trappist-1 is a faint, cool red dwarf, its habitable zone is much closer to the star than our Sun's habitable zone. Despite their close orbits, Trappist-1d, E, F, and G are all considered to be within or very near this crucial region. This makes the system an unprecedented target in the search for extraterrestrial life. Finding one potentially habitable world is exciting, but finding 3 or 4 in the same system dramatically increases the odds of discovering life, even if only microbial, or at least a planet capable of supporting it. This multitude of targets offers a unique opportunity for comparative planetology, allowing scientists to study how slight variations in orbital position and planetary history might influence a world's potential for habitability. The close orbits and the faintness of the star also mean that the planets are very likely to be tidally locked. Tidal locking is a phenomenon where a planet's rotation period matches its orbital period, meaning one side of the planet always faces its star, while the other side remains in perpetual darkness. Our own moon is tidally locked to Earth, always showing us the same face. For the Trappist-1 planets, this would create a permanent day side, a permanent night side, and a twilight zone or terminator region in between, where the sun would always hang low on the horizon. This could lead to extreme temperature differences across the planet's surface. However, scientific models suggest that thick atmospheres or vast oceans could help to redistribute heat from the day side to the night side, potentially moderating temperatures and making a larger portion of the planet hospitable. This unique characteristic adds another layer of complexity and fascination to the study of these worlds, requiring new models and theories for planetary climates that differ significantly from Earth's. From a scientific perspective, the Trappist-1 system is a dream come true for astrobiologists and planetary scientists. The sheer number of Earth-sized planets, their close proximity, and the fact that several are in the habitable zone provide a rich target for follow-up observations. It allows researchers to investigate questions that were previously impossible to explore with single exoplanet discoveries. How do planetary atmospheres evolve in such a system? Can life emerge on multiple worlds within the same system, perhaps even influencing each other? The system offers a natural laboratory for comparative studies, allowing scientists to look for commonalities and differences between worlds that formed in the same cosmic neighborhood. The consistent size and rocky composition of the planets, combined with their resonant orbits, suggest a shared formation history, making them excellent candidates for understanding the general processes of planet formation around red dwarfs. The discovery of the Trappist-1 system has profoundly impacted the search for life beyond Earth. It has shifted some of the focus from sun-like stars to the more numerous red dwarfs, highlighting them as promising candidates for hosting life. While red dwarfs present unique challenges for habitability, such as stellar flares and tidal locking, their extreme longevity, trillions of years far surpassing our sun's lifespan, offers an immense timescale for life to emerge and evolve. The Trappist-1 system is therefore not just a collection of 7 Earth-sized planets, it is a profound testament to the diversity of planetary systems in our galaxy, and a powerful beacon in humanity's quest to understand whether we are alone in the universe. Each of these sister worlds, spinning in their tight rhythmic dance around their faint red sun, holds the potential for incredible discoveries, pushing the boundaries of our knowledge and inspiring future generations to continue looking up at the sky with wonder and determination. In the remarkable ensemble of the Trappist-1 system, where 7 Earth-sized planets perform a tightly choreographed cosmic dance, the innermost world, Trappist-1b, occupies a position of extreme proximity to its faint red star. While it shares the Earth-like dimensions that make the system so compelling, its incredibly close orbit dictates an environment that is anything but Earth-like, pushing the boundaries of what we understand about planetary conditions. Trappist-1b is a world of perpetual scorching heat, likely devoid of the liquid water that defines habitability as we know it. Yet its study provides crucial insights into the extreme end of exoplanetary environments and the complex interplay between a star and its closest orbiting companions. Understanding this fiery world is essential for appreciating the diverse nature of the Trappist-1 family and the delicate balance required for potential life on its more distant siblings. Trappist-1b is the very first planet in the system, orbiting nearest to the star. Its orbital period is astonishingly short, completing 1 full revolution around Trappist-1 in just over 1 Earth day, specifically about 1.5 Earth days. To put this into perspective, our own innermost planet, Mercury, takes 88 Earth days to complete a single orbit around the Sun. This means that a year on Trappist-1b is less than 2 Earth days long. This incredibly rapid orbit is a direct consequence of its extreme proximity to the star. It circles Trappist-1 at a distance of only about 1 million miles, or 1.6 million kilometers. In comparison, Mercury orbits our Sun at an average distance of about 36 million miles, or 58 million kilometers. This illustrates the staggering difference in scale between the Trappist-1 system and our own, highlighting how tightly packed these 7 sister worlds are around their diminutive star. Because it orbits so close to Trappist-1, Planet B is subjected to an immense amount of radiation from its parent star, despite the star itself being faint compared to our Sun. The amount of energy it receives, known as stellar flux, is roughly 4 times the amount of energy Earth receives from the Sun. Even though Trappist-1 is a cool red dwarf, radiating mostly in the infrared, this close distance means that Planet B is constantly bathed in a relentless stream of energy. This intense radiation translates directly into exceptionally high surface temperatures, making it an inferno compared to the temperate conditions on Earth. Initial calculations, assuming no atmosphere, suggest that its equilibrium temperature would be around 400 Kelvin, or approximately 260 degrees Fahrenheit, well above the boiling point of water. This extreme heat means that liquid water, a fundamental requirement for life as we know it, cannot exist on the surface of Trappist-1b. Any water present during the planet's formation or early history would have long since boiled away, evaporating into the atmosphere and then potentially escaping into space due to the star's powerful radiation and stellar winds. This process is known as a runaway greenhouse effect, similar to what is thought to have occurred on Venus in our own solar system, but likely even more extreme given Trappist-1b's closer proximity to its star and the Red Dwarf's tendency to emit powerful flares. If Trappist-1b ever had an ocean, it would have transformed into a thick, superheated steam atmosphere, which would then be gradually stripped away over billions of years. The surface of Trappist-1b is therefore expected to be a barren, scorching landscape. Without a significant atmosphere to redistribute heat, the side permanently facing the star would be intensely hot, while the permanently dark night side, if it exists as distinct from an atmosphere that could redistribute heat, would be incredibly cold, although likely not as cold as an airless body due to any lingering atmospheric effects. However, given the high likelihood of a runaway greenhouse effect, it is more probable that if any atmosphere remains, it would be a dense, hot, and suffocating layer, potentially composed of heavy gases like carbon dioxide or even exotic volcanic gases. The intense stellar radiation would also play a role in altering the chemistry of any remaining atmosphere, breaking down molecules and creating a hostile environment. Like its sibling planets in the Trappist-1 system, Trappist-1b is almost certainly tidally locked to its star. This means that one side of the planet always faces the Red Dwarf, experiencing eternal daylight, while the other side is locked in eternal night. For Trappist-1b, this tidal locking would create an extremely harsh environment. The day side would be relentlessly irradiated and baked, possibly even experiencing volcanism due to extreme internal heating from tidal forces. The night side, if it were not for atmospheric circulation, would be perpetually frozen. However, with the high temperatures and potential for a dense atmosphere, any atmospheric circulation would likely be violent, with strong winds attempting to redistribute heat around the planet, leading to extreme weather patterns. The concept of a terminator line or twilight zone, where temperatures might be moderate, as often discussed for tidally locked planets in the habitable zone, is unlikely to apply to Trappist-1b due to its overwhelming heat budget. Despite its inhospitable conditions for life, Trappist-1b is of immense scientific interest. Its study helps astronomers understand the limits of planetary habitability. By examining the conditions on such an extreme world, scientists can better define the boundaries of the habitable zone and the factors that prevent a planet from retaining water or developing a stable atmosphere. It serves as a contrast to the potentially more temperate planets further out in the system, allowing for comparative studies of planetary evolution under varying stellar fluxes and tidal forces. Understanding why Trappist-1b is uninhabitable helps us appreciate what makes other planets potentially habitable. Furthermore, Trappist-1b is an excellent target for atmospheric studies using the James Webb Space Telescope. Even though it is likely to have a very thin or stripped atmosphere, or one dominated by heavy elements, Webb's ability to detect even trace amounts of gases can provide crucial information about its history and composition. Studying its atmospheric properties could reveal how much water, if any, it lost over billions of years, and what gases currently comprise its thin envelope. These observations would help validate or refine models of planetary atmospheric escape and evolution around active red dwarf stars. The insights gained from Trappist-1b can then be applied to understanding the more elusive atmospheres of the planets in the habitable zone. The extreme proximity of Trappist-1b also means it experiences significant tidal forces from its star. These forces can cause internal heating, similar to how Jupiter's moon Io is volcanically active, due to the immense tidal forces from Jupiter. While Trappist-1b is a planet and not a moon, the gravitational stretching and squeezing from its star could contribute to its internal heat budget and potentially drive geological activity. Scientists are investigating whether this tidal heating could play a role in outgassing any remaining volatiles or shaping the planet's internal structure. Its Earth-like size, confirmed by transit depth measurements and transit timing variations, means it is a rocky body, providing a foundation for such geological processes. Its density, though, is slightly lower than Earth's, suggesting a potentially different bulk composition or internal structure compared to our home planet. In the tightly wound cosmic spring of the Trappist-1 system, where 7 terrestrial worlds orbit their faint red star in a close-knit arrangement, Trappist-1c takes its place as the second planet out from the central sun. While it is certainly a fascinating world, positioned just beyond its blazing innermost sibling Trappist-1b, it nonetheless exists in a realm too intensely heated for the sustained presence of liquid water on its surface. Its orbital dance around Trappist-1 is slightly more leisurely than that of Planet B, yet it remains a swift journey by our solar system standards, underscoring the extreme compactness of this remarkable stellar family. Understanding Trappist-1c provides a crucial stepping stone in the scientific exploration of this system, allowing astronomers to delineate the unforgiving inner boundaries of habitability and to model the atmospheric conditions that might prevail on worlds perpetually scorched by their close-by stars. Trappist-1c completes one full orbit around its star in approximately 2.42 Earth days. This is still an incredibly rapid year, less than 3 Earth days long, showcasing the dizzying speed at which these planets hurtle through their tiny cosmic circuit. To put this into context, its orbital period is nearly exactly 3/2 of Planet B's period, a precise mathematical relationship that is part of the system's intricate orbital resonance. This resonance, a harmonious gravitational lockstep between the planets is a defining characteristic of the Trappist-1 system, influencing their long-term stability and internal dynamics. Planet C is situated at an average distance of about 2 million miles, or 3.2 million kilometers, from its star. While this is marginally further out than Planet B, it remains a mere fraction of the distance between our Sun and Mercury, which averages around 36 million miles. This small increase in distance, though significant in cosmic terms, is not enough to pull Trappist-1c out of the infernal grip of its star's intense radiation. The amount of energy that Trappist-1c receives from its star is a critical factor in determining its surface temperature, and consequently, its potential to host liquid water. Scientists calculate this energy intake in terms of stellar flux. Trappist-1c receives roughly 2 times the amount of energy per square foot that Earth receives from our Sun. While this is less than the 4 times experienced by Planet B, it is still a substantial amount of incoming radiation from a star that, despite its dimness in visible light, emits a significant portion of its energy in the infrared. This high stellar flux means that if Trappist-1c possessed no atmosphere, its equilibrium temperature would be in the range of 380 Kelvin to 400 Kelvin, or between 225 and 260 degrees Fahrenheit. These temperatures are well above the boiling point of water at standard atmospheric pressure, indicating that liquid water cannot stably exist on its surface. Given these scorching temperatures, any water that might have been present on Trappist-1c during its formation or early history would have likely evaporated and become part of a thick, steamy atmosphere. This process is known as a runaway greenhouse effect. Here is how it unfolds. As a planet warms, any liquid water on its surface begins to evaporate, increasing the amount of water vapor in its atmosphere. Water vapor is a powerful greenhouse gas, meaning it traps heat. As more water evaporates, the atmosphere traps more heat, leading to further warming, which in turn causes more water to evaporate. This positive feedback loop spirals out of control, eventually boiling away all surface water and creating an atmosphere dominated by superheated steam. This is the fate believed to have befallen Venus in our own solar system, and Trappist-1c, with its even higher stellar flux from a red dwarf, would be a prime candidate for a similar or even more extreme scenario. If Trappist-1c indeed underwent a runaway greenhouse process, its atmosphere today would be a dense, opaque blanket of steam, possibly mixed with other heavy gases like carbon dioxide and sulfur compounds released from volcanic activity. Such an atmosphere would exert immense pressure on the surface, making it an incredibly harsh and uninhabitable environment. The planet would be enveloped in thick clouds of water vapor, reflecting some incoming starlight, but also trapping a significant amount of heat. The high temperatures and pressures would create a dynamic, turbulent atmosphere, with fierce winds and perhaps a perpetual planet-wide rain of superheated water, evaporating before it even reaches the ground. The constant bombardment of high-energy radiation and stellar winds from Trappist-1, particularly during flare events common to young red dwarfs, would also contribute to the stripping away of this atmosphere over billions of years, slowly eroding its volatile components into space. Like its inner neighbour, Trappist-1c is almost certainly tidally locked to its star. This means one side of the planet perpetually faces Trappist-1, experiencing eternal daylight, while the opposite side remains in perpetual darkness. The concept of a terminator line, or twilight zone between these extremes, where temperatures might be moderate, is often discussed for tidally locked planets within the habitable zone. However, for a world like Trappist-1c, pushed to such high temperatures by its stellar flux, the entire atmosphere would likely be hot and dense. Any heat redistribution by atmospheric circulation would merely lead to a uniformly hot planet, with perhaps slightly cooler, but still scorching temperatures on the night side. The permanent day side would be relentlessly baked, while the night side, if it were not for atmospheric circulation, would be perpetually frigid. The dense, steamy atmosphere would act as a heat transfer mechanism, preventing the night side from freezing solid, but still leaving it incredibly warm. The strong tidal forces from the star could also cause significant internal heating within Planet C, potentially driving geological activity like volcanism, which could further contribute to the atmospheric composition by releasing gases from the planet's interior. The rocky nature of Trappist-1c has been confirmed through transit timing variations. By observing the subtle gravitational nudges it exerts on its neighbouring planets and receives in return, scientists have been able to estimate its mass. Its mass is roughly 85% that of Earth, and when combined with its radius of about 101% of Earth's radius, this yields a density very similar to Earth's. This high density strongly suggests that Trappist-1c is a rocky planet, composed of silicates and metals, rather than a gas giant or an icy world. This makes its current hot dry state or superheated steamy state a result of its stellar environment rather than its intrinsic composition. Its solid rocky surface would, however, be hidden beneath the thick opaque shroud of its dense atmosphere, a stark contrast to the familiar landscapes of Earth. While Trappist-1c is not considered a candidate for hosting life, it holds significant scientific value for several reasons. Firstly, it serves as a critical data point for understanding the inner edge of the habitable zone around red dwarf stars. By observing its atmospheric composition and properties with advanced telescopes like the James Webb Space Telescope, astronomers can test and refine models of planetary climate and atmospheric evolution. For instance, detecting significant amounts of water vapour, carbon dioxide or sulfur compounds would support the runaway greenhouse scenario. The absence of certain gases, or the presence of others, could challenge or confirm existing theories about how atmospheres respond to intense stellar radiation from a red dwarf. It helps define the conditions under which a planet loses its water and becomes inhospitable. Secondly, the study of Trappist-1c contributes to our understanding of the long-term evolution of planetary atmospheres. Red dwarfs are known to be particularly active in their youth, emitting powerful flares that can strip away planetary atmospheres. By examining the current state of Trappist-1c's atmosphere, scientists can gain insights into the cumulative effects of billions of years of stellar activity on a close-in planet. This is crucial for assessing the long-term habitability of the more distant Trappist-1 planets. If Planet C has managed to retain a substantial atmosphere, even a hot one, it might suggest that some close-in planets can indeed hold onto their gaseous envelopes despite harsh conditions. Finally, Trappist-1c's precise orbital resonance with its neighbours provides a unique laboratory for studying planetary dynamics. The gravitational interactions are strong enough to cause measurable changes in transit times, allowing for extremely precise measurements of its mass and the masses of its siblings. This intricate dance reveals details about the formation and migration history of the entire system. Each planet, including Trappist-1c, plays a role in stabilizing the orbits of its neighbours through these resonances, preventing the system from devolving into chaos. This tightly choreographed ballet has allowed the system to remain stable for billions of years, providing a long-term, if very hot, home for Planet C. Although its surface may be a searing, watery inferno or a desolate, baked rock, Trappist-1c remains an invaluable piece of the puzzle in unlocking the secrets of planetary systems beyond our own. Its hot, steamy embrace serves as a powerful reminder of the delicate balance required for conditions suitable for life. Among the extraordinary retinue of 7 Earth-sized worlds orbiting the faint red star Trappist-1, Planet D occupies a singularly intriguing position. It sits right at the inner edge of what astronomers define as the habitable zone. This delicate location makes Trappist-1d a world of immense scientific interest, embodying the fine line between a planet that is too hot to sustain liquid water on its surface, and one that might just possess the conditions necessary for life as we understand it. Its proximity to the star means it skirts the very brink of a runaway greenhouse effect, a fate that likely befell its inner neighbours, Trappist-1b and C. The study of Trappist-1d is therefore crucial for understanding the precise boundaries of habitability around red dwarf stars, offering a natural laboratory to explore the complex interplay of stellar radiation, planetary atmospheres, and the potential for liquid water. Trappist-1d is the third planet in the system, orbiting Trappist-1 in approximately 4.05 Earth days. This swift orbital period, just over 4 Earth days, continues the trend of incredibly short years within this compact system. It is part of the system's intricate orbital resonance chain, with its period being roughly 2/3 that of Planet E. This resonant dance ensures the long-term stability of the system, even with the planets packed so closely together. Trappist-1d orbits its star at an average distance of about 2.7 million miles, or 4.3 million kilometers. While still very close to its star by our solar system standards, this distance is significantly greater than that of its inner siblings, Trappist-1b and c, providing a crucial reduction in the amount of incoming stellar radiation. The amount of energy Trappist-1d receives from its star is a subject of intense focus. It receives approximately 110% of the stellar flux that Earth receives from our Sun. This seemingly small difference from Earth's energy budget is deceptive because Trappist-1 is a much cooler star than our Sun, emitting most of its light in the infrared part of the spectrum. This means that while the total energy received is comparable to Earth's, the spectral distribution of that energy is very different, with more heat and less visible light. If Trappist-1d had no atmosphere, its equilibrium temperature would be around 282 Kelvin, or approximately 48 degrees Fahrenheit. This temperature is below the freezing point of water, but relatively close to it, highlighting the planet's position on the borderline. However, a planet's actual surface temperature is heavily influenced by its atmosphere, particularly the presence and concentration of greenhouse gases. This is where the fine line for Trappist-1d truly comes into play. For a planet to sustain liquid water, it needs to have an atmosphere that can create a greenhouse effect, trapping some of the star's heat and raising the surface temperature above freezing. Earth's atmosphere, with its natural greenhouse effect, keeps our planet warm enough for liquid water to exist. On Trappist-1d, a moderate amount of greenhouse gases like carbon dioxide and water vapor could potentially warm the planet sufficiently to allow for stable liquid water on its surface. However, too much of these gases could tip the balance, leading to a runaway greenhouse effect like that on Venus, or, more likely, on Trappist-1c, boiling away all surface water. Conversely, too little greenhouse gas would leave the planet a frozen, icy wasteland, unable to melt any significant amounts of surface ice into liquid. Scientists have explored various atmospheric scenarios for Trappist-1d. One possibility is a water world with extensive oceans, where the presence of a sufficient amount of water vapor and other greenhouse gases creates a stable, temperate climate. Another scenario posits a desert planet with very limited surface water, perhaps only in polar regions or in specific low-lying areas, with most of the planet being dry and rocky. A third possibility is an eyeball planet, a term sometimes used for tidally locked worlds, where the day side might be too hot and dry, the night side too cold and icy, but a narrow ring of liquid water could exist in the twilight zone between the two extremes. The precise atmospheric composition and thickness would determine which of these scenarios, or others, best describes Trappist-1d. Like all the planets in the Trappist-1 system, Planet D is expected to be tidally locked to its star. This means it has a permanent day side facing the Red Dwarf and a permanent night side eternally shrouded in darkness. For a planet at the inner edge of the habitable zone, tidal locking introduces significant challenges for habitability. The day side would be constantly irradiated, potentially leading to high temperatures, while the night side would be perpetually cold. However, an adequate atmosphere could play a crucial role in redistributing heat from the day side to the night side through strong winds and atmospheric circulation. This global atmospheric transport could moderate the extreme temperatures, creating a more uniform and potentially habitable climate across a larger portion of the planet, particularly in the Terminator region. Vast oceans, if present, could also contribute to heat redistribution through ocean currents. The density of Trappist-1d is an important clue to its composition. Its mass is estimated to be about 30% of Earth's mass, making it the least massive of the Trappist-1 planets. Its radius is about 78% of Earth's radius. This combination yields a density that is significantly lower than Earth's, suggesting that Trappist-1d might have a substantial amount of water or other lighter volatile compounds in its composition. Some models indicate that it could be up to 5% water by mass, potentially hosting a global ocean or a significant ice layer beneath a thin atmosphere. This contrasts with Earth, which is only about 0.02% water by mass. The lower density of Trappist-1d makes it a compelling candidate for a water world or a planet with a deep subsurface ocean, even if its surface conditions prove to be too harsh for liquid water. The study of Trappist-1D's atmosphere is a high priority for astronomers, particularly with the capabilities of the James Webb Space Telescope. By observing the star's light as it passes through Planet D's atmosphere during transits, Webb can perform transmission spectroscopy to search for specific gases. Detecting significant amounts of water vapour, carbon dioxide or methane would be important, as these are key greenhouse gases. The presence of oxygen, especially in large quantities, could be a compelling biosignature, though false positives from abiotic processes must always be considered. Even without discovering biosignatures, simply characterizing the atmosphere would provide invaluable data for climate models of exoplanets around red dwarfs, and for refining our understanding of the inner edge of the habitable zone. If Trappist-1D shows evidence of a stable, moderate atmosphere, it would greatly expand our understanding of how life could survive in such tightly packed stellar systems. The active nature of the parent star, Trappist-1, poses a significant challenge for the habitability of Planet D. Red dwarfs, especially in their youth, are prone to powerful stellar flares and bursts of high-energy radiation. These events could potentially erode a planet's atmosphere over billions of years, or deliver lethal doses of radiation to any surface life. For Trappist-1D, located so close to the star, a strong planetary magnetic field would be absolutely crucial to shield its atmosphere from these onslaughts. The existence and strength of such a magnetic field depend on the planet's internal structure and dynamics, which are currently unknown. Understanding how Trappist-1D has managed to retain any atmosphere, or if it has, in the face of these stellar storms, is a key area of research. Trappist-1D's place at the borderline of habitability makes it a natural testbed for various planetary climate models. Scientists can use it to explore how different atmospheric compositions, cloud formations, and internal heat sources interact to shape a planet's environment. It represents a critical point in the transition from the scorching inner worlds to the potentially more temperate outer worlds of the system. Its existence forces astronomers to refine their definitions of the habitable zone, moving beyond simple distance from the star to consider factors like the star's spectral type, flare activity, and the complex atmospheric dynamics of tidally locked planets. The insights gained from studying Trappist-1D will not only shed light on this specific world, but will also inform the search for life on thousands of other exoplanets orbiting red dwarfs throughout our galaxy. It is a world on the edge, a fascinating testament to the diverse range of planetary environments that exist beyond our familiar solar system, beckoning scientists to unravel its secrets. Among the 7 remarkable worlds that gracefully orbit the faint red star Trappist-1, Planet E holds a particularly prominent position in the minds of scientists and dreamers alike. It is arguably the most promising candidate in the entire system for harbouring liquid water on its surface, and consequently, for potentially hosting life as we know it. Located firmly within the star's habitable zone, Trappist-1e represents a beacon of hope in humanity's ongoing quest to discover extraterrestrial biology. Its study is not merely an academic exercise, it is a profound exploration into the conditions that might allow life to flourish in environments vastly different from our own, yet still fundamentally reliant on the presence of that most crucial ingredient, water. To understand the profound possibilities of this world, we must delve into its orbital characteristics, its environmental conditions, and the intricate dance between its atmosphere, its internal dynamics, and the light from its faint red sun. Trappist-1e completes one full orbit around its star in approximately 6.10 Earth days. This means its year is just a little over 6 Earth days long, a remarkably short duration compared to any planet in our own solar system. This swift revolution places it at an average distance of about 3.7 million miles, or 5.9 million kilometers, from Trappist-1. This distance, while seemingly minuscule when compared to the vast expanses of our own solar system, is precisely what positions Trappist-1 so favourably within its star's habitable zone. Because Trappist-1 is a much cooler and dimmer star than our Sun, its habitable zone is much closer in. Trappist-1e receives just the right amount of stellar energy to potentially allow for liquid water to exist on its surface, assuming it possesses an adequate atmosphere. The amount of energy, or stellar flux, that Trappist-1e receives from its star is very similar to what Earth receives from our Sun. Scientists estimate it gets about 94% of the stellar flux Earth receives. This is a critical factor, suggesting that its surface temperature, if protected by an atmosphere, could be well within the range where water can remain in liquid form. If it had no atmosphere, its equilibrium temperature would be around 251 Kelvin, or about -8 degrees Fahrenheit. This temperature is below freezing, highlighting the absolute necessity of an atmosphere to warm the planet sufficiently for liquid water. A moderately effective greenhouse effect, similar to or slightly stronger than Earth's, could easily raise its average surface temperature above the freezing point of water, enabling the existence of lakes, rivers, or even global oceans. The density of Trappist-1e provides compelling evidence that it is a rocky world, much like Earth. Through meticulous analysis of the subtle gravitational interactions between the planets, particularly the transit timing variations, astronomers have determined its mass to be approximately 77% that of Earth. When combined with its estimated radius, which is about 92% of Earth's radius, its density comes out to be very close to Earth's density. This indicates that Trappist-1e is not a gas giant, nor is it a lightweight icy world. Rather, it is a solid, terrestrial body, likely composed of silicates and metals in similar proportions to our own planet. This rocky composition is a prerequisite for a solid surface where liquid water could pool and where land-based life could potentially emerge. Like all the other planets in the Trappist-1 system, Trappist-1e is almost certainly tidally locked to its star. This means that one side of the planet perpetually faces Trappist-1, experiencing eternal daylight, while the opposite side remains in perpetual night. The region between these two extremes, known as the terminator line or twilight zone, would experience perpetual sunrise or sunset. This unique orbital configuration creates significant challenges for habitability, but also fascinating possibilities. The day side would be constantly warmed by the star, while the night side would constantly radiate heat into space, potentially becoming very cold. However, the presence of a substantial atmosphere on Trappist-1e could play a vital role in moderating these extreme temperatures. A thick enough atmosphere could redistribute heat from the scorching day side to the freezing night side through powerful global winds and atmospheric currents. This atmospheric circulation would act as a planetary thermostat, evening out the temperatures and potentially making a much larger portion of the planet habitable. Models suggest that such an atmosphere could lead to a temperate eyeball planet, with a permanent ocean covering the day side, possibly freezing over on the night side, or a more uniformly habitable world with robust atmospheric transport. The specific composition and thickness of this atmosphere would be crucial determinants of its climate. For example, a carbon dioxide-rich atmosphere would trap more heat, potentially allowing for liquid water over a wider range of surface temperatures. If Trappist-1e indeed harbours liquid water, the possibilities for its surface conditions are diverse and intriguing. It could be a true water world, almost entirely covered by a vast deep ocean with perhaps only small islands or submerged continents. Such a world might have thriving marine ecosystems, perhaps including complex life forms adapted to its unique conditions. Alternatively, it could have a more Earth-like distribution of land masses and oceans, creating continents, mountains and valleys sculpted by geological forces and the flow of water. The interaction between liquid water and a rocky surface over billions of years is fundamental to many of Earth's life-sustaining cycles, including the carbon cycle, which helps regulate climate. The presence of water also enables chemical reactions necessary for the origin and evolution of life. The long-term habitability of Trappist-1e also depends on the presence and strength of a planetary magnetic field. Red dwarf stars, particularly in their youth, are known to be prone to powerful stellar flares and bursts of high-energy radiation. These events can be many times more energetic than flares from our Sun, and could potentially strip away a planet's atmosphere over billions of years, or deliver lethal doses of radiation to any surface life. A strong internal dynamo, similar to Earth's, would generate a protective magnetic field that could deflect these harmful particles, preserving the atmosphere and shielding the surface from radiation. The existence of such a magnetic field on Trappist-1e is currently unknown, but it is a critical factor for its long-term potential to sustain life. scientists are actively working on models to understand the internal structure of these planets and whether they are likely to generate magnetic fields. The ultimate quest for Trappist-1e is the search for signs of life, or biosignatures, in its atmosphere. With the launch of the James Webb Space Telescope, astronomers now have an unparalleled tool to investigate the atmospheres of these distant worlds. By observing the star's light as it filters through Trappist-1e's atmosphere during a transit, Webb can perform highly sensitive transmission spectroscopy. This technique allows scientists to identify the chemical composition of the atmosphere, the detection of certain gases, particularly oxygen, methane, ozone, or specific combinations of these gases, in quantities that cannot be explained by non-biological processes, would be strong indicators of biological activity. For example, oxygen is highly reactive and would quickly disappear from an atmosphere without continuous replenishment, such as that provided by photosynthesis on Earth. The presence of both oxygen and methane together is considered particularly compelling, as these gases tend to react with each other unless constantly produced by life. However, the interpretation of biosignatures around red dwarfs can be complex. The unique light spectrum of a red dwarf, with its abundance of infrared radiation, might favour different types of photosynthesis than those on Earth. Furthermore, the active nature of red dwarfs, with their frequent flares, could potentially produce or destroy certain atmospheric gases in ways that might mimic or obscure biosignatures. Thus, any potential detection of biosignatures would require extensive follow-up observations and careful analysis to rule out false positives. Nevertheless, Trappist-1e stands out as a prime target for these groundbreaking observations, offering the best chance yet to find the atmospheric fingerprints of alien biology. Beyond the scientific technicalities, the notion of Trappist-1e as a potential water world evokes a profound sense of wonder. Imagine a planet where the sky might always be tinged red by its star, where another world might hang large in the sky, and where life might have evolved under conditions so different from our own. What forms would such life take? Would it be microbial, hidden beneath a vast ocean, or perhaps multicellular, adapted to the dim red light and the unique climate of a tidally locked world? The very existence of Trappist-1e, so similar in size to Earth and seemingly positioned in a cosmic sweet spot, provides tangible evidence that the universe might indeed be teeming with worlds capable of sustaining life. It offers a powerful reminder that our own Earth, while precious and unique, may not be an anomaly, but rather one example among countless possibilities for planetary habitation across the vast expanse of the cosmos. The ongoing study of Trappist-1e is a journey into these possibilities, a scientific endeavour driven by both rigorous data and an enduring human curiosity about our place in the universe. Continuing our exploration of the extraordinary Trappist-1 system, we now turn our attention to Planet F, a world that stands as another compelling candidate for habitability. Positioned further out in the star's habitable zone than Trappist-1e, Planet F offers a glimpse into a potentially cooler and perhaps icier realm, where liquid water could still persist, possibly hidden beneath a thick crust of ice. Its study complements that of Trappist-1e, providing a broader understanding of the range of conditions within the habitable zone of a red dwarf star and expanding our notions of where and how life might thrive in the universe. Trappist-1 embodies the possibility of a cool, wet world, a testament to the diverse expressions of habitability that might exist beyond our familiar Earth. Trappist-1F completes one orbit around its star in approximately 9.21 Earth days. This extends its year to just over 9 Earth days long, making it a slightly more leisurely traveller than its inner siblings. This longer orbital period places it at an average distance of about 4.8 million miles, or 7.7 million kilometres, from Trappist-1. While still incredibly close to the star in terms of our solar system's scale, this greater distance means it receives less stellar energy compared to planets D and E, making it a cooler world. Trappist-1 is situated deeper into the habitable zone, toward its outer, cooler edge, rather than its inner, warmer edge. The amount of stellar flux Trappist-1F receives from its parent star is estimated to be around 63% of the energy Earth receives from the Sun. This lower energy input immediately suggests a cooler environment. If Trappist-1F had no atmosphere, its equilibrium temperature would be approximately 219 Kelvin, or about minus 65 degrees Fahrenheit. This temperature is well below the freezing point of water, indicating that an atmosphere with a substantial greenhouse effect is absolutely essential for liquid water to exist on its surface. Without such an atmospheric blanket, Trappist-1F would be a frozen, desolate ice ball. However, with the right atmospheric composition and density, enough heat could be trapped to raise surface temperatures above freezing, at least in certain regions or during certain periods. Like its sibling planets, Trappist-1F is believed to be a rocky world. Its mass is estimated to be approximately 104% of Earth's mass, making it slightly more massive than our planet. Its radius is about 103% of Earth's radius, indicating it is also slightly larger. When these figures are combined, they yield a density very similar to Earth's, confirming its terrestrial composition. This means Trappist-1F is not a gas giant or a purely icy body, but rather possesses a solid, rocky core and mantle, providing a stable foundation for the potential presence of water. This rockiness is crucial as it provides a surface for water to accumulate and the possibility of geological activity, such as volcanism, which can release gases into the atmosphere and cycle nutrients, processes thought to be vital for long-term habitability. Given its cooler position within the habitable zone, Trappist-1F is a prime candidate for being a cool, wet world. This could manifest in several ways. One possibility is a planet with extensive ice caps, or even a global ice shell, similar to a snowball Earth scenario from our planet's distant past. However, beneath this icy exterior, there could be vast liquid oceans, warmed either by geothermal activity from the planet's interior or by tidal heating from the gravitational tugs of its star and neighbouring planets. This scenario, with a subsurface ocean, is analogous to some of the fascinating icy moons in our own solar system, such as Jupiter's moon Europa or Saturn's moon Enceladus, which are believed to harbour subsurface oceans beneath kilometres of ice, heated by tidal forces from their gas giant parents. Another possibility for Trappist-1F is a world with a surface ocean that is prone to freezing, perhaps with seasonal melting or regions that remain liquid due to strong atmospheric heat transport. The presence of a thick, greenhouse-rich atmosphere would be critical in such a scenario, helping to trap enough warmth to maintain liquid water. This atmosphere would have to be robust enough to prevent the entire planet from freezing solid, especially on the tidally locked night side. For a tidally locked world like Trappist-1F, the perpetual night side would be extremely cold, potentially leading to the formation of massive ice sheets or glaciers. The day side, however, constantly warmed by the faint red star, could sustain liquid oceans. The transition zone, or terminator between day and night, could be a slushy, dynamic region of melting and refreezing ice. The specific atmospheric composition of Trappist-1F is key to its potential habitability. For a cooler world, a significant greenhouse effect would be necessary to raise its surface temperature above freezing. Gases like carbon dioxide and water vapour would be crucial. If Trappist-1F has a thick atmosphere rich in these gases, it could create a warm enough blanket to keep liquid water stable. However, the origin and long-term stability of such an atmosphere around an active red dwarf star remain important questions. A magnetic field would be vital to protect this atmosphere from erosion by stellar winds and powerful flares, which are more common in red dwarfs, especially early in their lives. Without a strong magnetic shield, even a thick atmosphere could be gradually stripped away over billions of years, leaving a cold, barren world. The long lifespan of Trappist-1, lasting for trillions of years, provides an immense timescale for geological processes and the evolution of a stable atmosphere on planet F. Over such vast periods, even infrequent volcanic activity could gradually release greenhouse gases, contributing to a warming atmosphere. The interplay between internal heat, tidal forces, and atmospheric composition would determine the planet's ultimate climate. If it hosts a subsurface ocean, tidal heating could be crucial, constantly churning the interior and maintaining the liquid state of the water, potentially providing energy and nutrients for life that might exist in such a deep, dark environment, similar to the chemosynthetic ecosystems found around hydrothermal vents on Earth's ocean floor. The search for life on Trappist-1F would likely involve looking for biosignatures in its atmosphere, using instruments like the James Webb Space Telescope. If it has a surface ocean, gases like oxygen or methane could indicate photosynthesis or other biological processes. If it harbours a subsurface ocean, direct detection of life would be much more challenging, requiring future missions capable of drilling through thick ice shells. However, indirect evidence such as signs of geological activity or specific chemical compounds in the atmosphere that might hint at an active interior could provide tantalizing clues about potential subsurface liquid water environments. The unique infrared emission of Trappist-1 also means that any photosynthetic life on planet F might utilize different wavelengths of light than Earth's plants, possibly leading to entirely new biological pigments and adaptations. The existence of Trappist-1F as a potentially cool and wet world significantly broadens our understanding of the conditions under which life might arise. It suggests that habitability is not confined to Earth-like planets, orbiting sun-like stars at a specific distance, but can extend to cooler worlds around red dwarfs, potentially even those with global ice covers hiding vast liquid oceans. This expands the cosmic real estate for life dramatically, given the sheer abundance of red dwarf stars in our galaxy. Trappist-1F presents a fascinating contrast to the potentially warmer, more exposed planet E, allowing scientists to compare and contrast the different facets of habitability within a single, extraordinary system. Its secrets, locked perhaps beneath an icy shell or shrouded by a persistent fog, patiently await the advanced observational capabilities that will one day pierce its mysteries, bringing us closer to understanding the true diversity of life's potential homes across the universe. In the captivating cosmic ballet of the Trappist-1 system, where 7 terrestrial worlds orbit their faint red star in a tight resonant formation, Trappist-1G holds a significant position. It is the 6th planet from the star and occupies a critical place towards the cooler outer boundary of the star's habitable zone. This makes Trappist-1G a compelling subject of study, a world where liquid water, a fundamental ingredient for life as we know it, could potentially exist, though perhaps in a state more akin to the icy moons of our outer solar system than to the verdant surfaces of Earth. Its potential as a cool, wet world challenges our conventional understanding of habitability, pushing us to consider environments where life might flourish under a thick canopy of ice, warmed by internal processes rather than direct sunlight. The investigation into Trappist-1G is therefore a journey into the potential diversity of life-supporting conditions, urging us to look beyond Earth-centric definitions of planetary warmth. Trappist-1G completes one full orbit around its star in approximately 12.35 Earth days. This means its year, though still remarkably short by Earth standards, is considerably longer than those of its inner siblings, reflecting its greater distance from the star. This relatively extended orbital period places Trappist-1G at an average distance of about 6.3 million miles, or 10.1 million kilometers, from Trappist-1. While this distance is still quite close when compared to planets in our own solar system, where even Mercury orbits at 36 million miles, it represents a substantial shift in the energy budget received from its parent star. This increased distance places it firmly at the outer limits of the stellar habitable zone, where incoming energy levels begin to dwindle, making it inherently a colder world. The amount of energy, or stellar flux, that Trappist-1G receives from its star is significantly less than what the inner planets experience. It is estimated to receive about 38% of the stellar flux that Earth receives from our Sun. This reduced energy input means that if Trappist-1G had no atmosphere, its equilibrium temperature would be approximately 208 Kelvin, or about minus 85 degrees Fahrenheit. These temperatures are far below the freezing point of water, indicating that the surface of Trappist-1G would likely be a perpetually frozen, icy landscape without a substantial atmospheric blanket. For any liquid water to exist on its surface, a very robust greenhouse effect, far stronger than Earth's, would be required to trap enough heat from the dim red star and warm the planet significantly. Without such an atmosphere, Trappist-1G would be a true ice ball, with its surface water frozen solid. The composition of Trappist-1G is crucial to understanding its potential. Through careful analysis of its gravitational interactions with its neighbouring planets, scientists have determined its mass to be approximately 134% that of Earth, making it the most massive planet known in the system. Its radius is about 112% of Earth's radius, making it also the largest planet in the system. When these values are combined, they yield a density that is slightly lower than Earth's. This lower density, combined with its position at the cooler edge of the habitable zone, strongly suggests that Trappist-1g likely contains a substantial amount of water, perhaps in the form of a thick ice mantle, or even a deep global ocean beneath a surface ice shell. Estimates suggest that water could make up a significant fraction of its total mass, possibly 5 to 10% or even more, in stark contrast to Earth's much smaller water content. This indicates a very wet world, even if that water is predominantly in solid form. Like all planets in the Trappist-1 system, Planet G is almost certainly tidally locked to its star. This means one side of the planet perpetually faces Trappist-1, experiencing eternal twilight, while the opposite side remains in eternal darkness. For a world at the cooler edge of the habitable zone, tidal locking intensifies the potential for extreme temperature differences. The permanent day side, though receiving modest stellar energy, might still be cold, potentially supporting a permanent ice sheet or snow cover. The permanent night side would be incredibly frigid, likely experiencing temperatures that would freeze most atmospheric gases solid, contributing to a substantial ice buildup. However, the intriguing possibility for Trappist-1g lies beneath its potentially icy surface. Scientists speculate that this world could harbour a vast subsurface ocean, a reservoir of liquid water hidden beneath a thick crust of ice. Such a subsurface ocean could be maintained in a liquid state by internal heat sources. One primary source of this heat would be tidal heating. As Trappist-1g orbits its star and interacts gravitationally with its neighbouring planets in their intricate resonance, the planet is constantly stretched and squeezed. This continuous flexing generates friction and heat within its interior, analogous to how Jupiter's moon Europa and Saturn's moon Enceladus are believed to maintain their subsurface oceans. This tidal heating could provide sufficient warmth to melt ice deep below the surface, creating a vast liquid realm, protected from the harsh radiation of the star and the cold vacuum of space. Another potential source of internal heat for Trappist-1g could be radiogenic heating, the decay of radioactive elements within its rocky core. Similar to Earth's interior, the decay of isotopes like uranium, thorium, and potassium generates heat, contributing to the planet's overall thermal budget. While tidal heating is likely the dominant source given its close proximity to the star and resonant interactions, radiogenic heating would provide a steady long-term source of warmth, complementing the tidal forces and helping to sustain a subsurface ocean over billions of years. This combination of heat sources would be crucial for maintaining liquid water in a perpetually dark and cold environment. If Trappist-1g indeed possesses a subsurface ocean, the implications for life are profound. Such an ocean would be shielded from the stellar flares and harmful radiation that might otherwise impact surface life. Life in a subsurface ocean would likely be chemosynthetic, meaning it would derive energy from chemical reactions rather than from sunlight. On Earth, vibrant chemosynthetic ecosystems thrive around hydrothermal vents at the bottom of our oceans, far removed from sunlight, utilizing chemical energy released from the Earth's interior. Similar processes could occur on Trappist-1g, where geological activity driven by internal heat could create hydrothermal vents on the ocean floor, providing energy and nutrients for a unique form of alien biology. This opens up the possibility of life flourishing in environments that are fundamentally different from Earth's surface, yet still reliant on liquid water and an energy source. The atmosphere of Trappist-1g, if present, would likely be quite different from Earth's. Given its cold surface, a substantial portion of any atmospheric gases, particularly water vapour, would condense and freeze out, forming ice on the surface. However, some heavier gases like carbon dioxide or methane could still persist, especially if released through volcanic activity or from the interaction of water with rock. The thickness and composition of this atmosphere would significantly impact the planet's overall heat balance and its ability to maintain any surface liquid water. Observing this atmosphere with the James Webb Space Telescope would be crucial. Even if the surface is frozen, detecting specific gases could provide clues about the planet's internal activity. The presence of a subsurface ocean or even potential biosignatures that might vent from a deep hidden biosphere. The challenge of detecting life on a world like Trappist-1G is immense. If life is confined to a subsurface ocean, direct observation would be impossible with current or near-future technology. It would require advanced probes capable of penetrating kilometers of ice to reach the liquid water below. However, indirect evidence might still be detectable. For instance, certain chemical compounds, if produced by a subsurface biosphere and subsequently vented into the atmosphere, could be detectable by sensitive telescopes. Or, distinctive geological features on the surface, such as cryovolcanism, ice volcanoes, driven by internal heat, could hint at an active interior and the presence of liquid water below. The subtle gravitational interactions with its neighbouring planets and the star itself could also provide insights into its internal structure and the presence of a significant liquid layer. Trappist-1G serves as a powerful reminder of the vast diversity of potentially habitable environments in the universe. It pushes the boundaries of our search for life beyond the Earth-like surface conditions we are familiar with, forcing us to consider worlds where life might exist in perpetual twilight or even complete darkness, sustained by processes other than photosynthesis. Its position at the outer edge of the habitable zone, coupled with its large size and likely high water content, makes it a fascinating case study for understanding cooler, water-rich exoplanets. As our observational capabilities continue to advance, Trappist-1G will remain a prime target, a world of potential hidden oceans, urging us to continue our ambitious exploration of the cosmic cold. Its very existence broadens the canvas upon which we might find the brushstrokes of alien biology. Within the compact yet incredibly diverse Trappist-1 system, where a family of 7 terrestrial planets orbits a faint red star, Trappist-1H occupies the outermost known position. It is the 7th and most distant planet discovered in this remarkable system. While it shares the Earth-like dimensions that make the Trappist-1 system so compelling, its remote location within the system, far beyond the star's habitable zone, dictates an environment of profound cold, a perpetually icy world where the conditions for liquid water on its surface are virtually non-existent. Trappist-1H serves as a critical marker in our understanding of planetary systems, defining the frigid outer boundary beyond which worlds become frozen wastelands, even if they are composed of a significant amount of water. Its study offers insights into the extremes of exoplanetary environments and the limits of where surface liquid water can persist. Trappist-1H completes one full orbit around its star in approximately 18.77 Earth days. This represents the longest orbital period of any known planet in the Trappist-1 system, reflecting its position as the furthest world from its star. Its year, therefore, is just under 19 Earth days long, a testament to the incredibly tight arrangement of this planetary family, where even the outermost member orbits its star more quickly than Mercury orbits our Sun. Trappist-1H orbits its star at an average distance of about 7.5 million miles, or 12.1 million kilometers. While still very close by solar system standards, this distance places it far enough from its faint red star to significantly reduce the amount of incoming stellar radiation, leading to extreme cold. The amount of energy, or stellar flux, that Trappist-1H receives from its parent star is exceedingly low, especially when compared to Earth. It is estimated to receive only about 20% of the stellar flux that Earth receives from our Sun. This dramatically reduced energy input means that if Trappist-1H had no atmosphere, its equilibrium temperature would be approximately 173 Kelvin, or about minus 150 degrees Fahrenheit. These temperatures are profoundly cold, far below the freezing point of water, and even below the freezing points of many other common volatile compounds. At such extreme temperatures, any water on its surface would be frozen solid, existing as rock-hard ice. Due to these frigid conditions, Trappist-1H is considered far beyond the habitable zone, meaning it is too cold to host liquid water on its surface. Even if Trappist-1H possessed a thick atmosphere filled with potent greenhouse gases, it would be extremely challenging, if not impossible, for such an atmosphere to trap enough heat to raise the surface temperature above the freezing point of water. At these cold temperatures, many gases, including water vapour and even carbon dioxide, would likely condense out of the atmosphere and freeze onto the surface as ice or frost. This process would effectively collapse any substantial atmosphere, leaving behind a very thin, tenuous envelope or perhaps no stable atmosphere at all. The very cold conditions would essentially freeze out most atmospheric components, leading to a barren, airless or near-airless world dominated by vast expanses of ice. The composition of Trappist-1H, however, indicates that it is a water-rich world, despite its frozen state. Its mass is estimated to be approximately 38% of Earth's mass, and its radius is about 75% of Earth's radius. These measurements result in a density that is significantly lower than Earth's. This lower density suggests that Trappist-1H, much like Planet G, is composed of a substantial fraction of water, but in its case nearly all of it would be in the form of ice. It is likely a rocky core surrounded by a very thick mantle of ice, perhaps extending for hundreds of miles beneath its surface. This composition makes it similar to some of the icy dwarf planets and moons in the outer reaches of our own solar system, such as Pluto or Neptune's moon Triton, which are characterized by vast ice fields and extremely low temperatures. Like all its sibling planets, Trappist-1H is almost certainly tidally locked to its star. This means one side of the planet always faces the dim red dwarf, experiencing eternal daylight, while the opposite side remains in perpetual darkness. For a world as cold as Trappist-1H, this tidal locking would lead to even more dramatic thermal differences. The day side would be constantly exposed to the meagre stellar flux, potentially maintaining a slightly warmer but still well below freezing temperature. The night side would be perpetually frigid, radiating what little heat it possesses into the cold vacuum of space, accumulating immense amounts of ice and potentially even frozen atmospheric gases. The distinction between day and night on such a cold, icy world would be stark, with vast glaciers and ice sheets stretching across its entire surface. While surface liquid water is considered highly unlikely for Trappist-1H, the possibility of a subsurface ocean cannot be entirely ruled out, though it is considered much less probable than for Planet G. Any subsurface ocean would need to be sustained by internal heat, primarily from tidal heating due to its gravitational interactions with Trappist-1 and its inner siblings, or from radiogenic heating from its core. However, given its greater distance from the star and its lower mass compared to Planet G, the tidal forces acting on Trappist-1H are likely much weaker. This means that if an ocean exists, it would likely be much deeper and smaller, or perhaps a mere slushy layer within its icy mantle. Such a deep, potentially isolated ocean would be incredibly challenging to detect and would represent an extremely niche environment for life. The atmosphere of Trappist-1H, if it has one, would be very thin and cold. At such low temperatures, most atmospheric gases would freeze out and condense onto the surface. Any atmosphere that did persist would likely be composed of very light gases that resist freezing, or perhaps gases released from occasional geological activity. This makes studying its atmosphere incredibly challenging, even for sensitive instruments like the James Webb Space Telescope. Observing Trappist-1H would primarily focus on characterizing its surface composition, looking for different types of ice, and perhaps inferring its internal structure from very precise measurements of its mass and gravitational field, which could indicate the presence of deep, heavy layers of rock and ice. Trappist-1H serves a crucial role in defining the outer edge of habitability for red dwarf systems. By studying its extremely cold, icy environment, astronomers can better understand the precise limits of where liquid water can exist, even in subsurface reservoirs. It helps to calibrate and refine climate models for exoplanets, showing the point at which a planet simply becomes too cold to support active hydrological cycles or a stable, thick atmosphere. It acts as a benchmark for characterizing cold, rocky exoplanets, which are likely very common given the vast number of red dwarf stars. Its barren, icy landscape stands in stark contrast to the tantalizing possibilities presented by its inner, warmer neighbors, highlighting the delicate balance of stellar energy and planetary properties required for the emergence of liquid water and potentially life. The universe, in its boundless complexity, presents us with phenomena that challenge our everyday understanding. Among the most fascinating and common occurrences in stellar systems beyond our own is a state known as tidal locking. This condition fundamentally alters a planet's rotation, fixing one face perpetually towards its star, much like our own moon always presents the same familiar face to Earth. This synchronous rotation, driven by the relentless gravitational ballet between a star and its orbiting worlds, is not merely a curious astronomical detail. It profoundly shapes the climate, geology, and potential for life on these distant planets. For the 7 sister worlds of the Trappist-1 system, their close orbits around a faint red dwarf make tidal locking an almost certain reality, fundamentally defining their environments and influencing their prospects for habitability. Understanding tidal locking is thus paramount to comprehending the unique characteristics of these compelling exoplanets. At its core, tidal locking is a consequence of gravity. Every celestial body exerts a gravitational pull on every other body. When one object orbits another, this gravitational force is not uniform across the orbiting body. The side of the orbiting body closest to the central mass experiences a stronger gravitational pull than the side farthest away. This difference in gravitational force creates a tidal bulge on both the near and far sides of the orbiting object, stretching it slightly along the line pointing towards the central body. On Earth, we famously observe this effect in our oceans, where the moon's gravity creates high and low tides. However, tides are not limited to oceans. They affect the solid body of a planet or moon as well, creating slight deformations in its shape. As a planet rotates, these tidal bulges are constantly trying to reorient themselves to align with the gravitational pull of the star. If the planet is rotating faster than it is orbiting, the bulges are dragged slightly ahead of the direct line to the star. The star's gravity then pulls back on these misaligned bulges, creating a torque, a twisting force, that acts to slow the planet's rotation. This braking action continues until the planet's rotation period matches its orbital period, a state of synchronous rotation where one side permanently faces the star. Once this state is reached, the tidal bulges are perfectly aligned with the star and the braking force ceases. The system reaches a state of minimum energy, a stable equilibrium where the planet is tidally locked. This process can take millions or even billions of years, depending on the masses of the star and planet, their distance, and the initial rotation rate of the planet. For the Trappist-1 planets, tidal locking is an almost inescapable fate due to several key factors. First, their parent star, Trappist-1, is a red dwarf, a star with significantly less mass than our Sun. While less massive, these stars are still immensely powerful gravitational sources. Second, and crucially, all 7 Trappist-1 planets orbit incredibly close to their star. The innermost planet, Trappist-1b, completes an orbit in just over 1 Earth day, and even the outermost planet, Trappist-1h, takes less than 19 Earth days to complete its orbit. This extreme proximity places them deep within the gravitational embrace of Trappist-1, exposing them to very strong tidal forces. The strength of tidal forces decreases rapidly with distance. They are inversely proportional to the cube of the distance between the two bodies. Therefore, planets orbiting very close to their stars experience immensely powerful tidal effects, accelerating the process of tidal locking. The initial rotation rates of planets formed in a protoplanetary disk are thought to be relatively fast. However, over hundreds of millions to billions of years, the relentless tidal braking action exerted by the star gradually saps the rotational energy from these close-in worlds. This energy is dissipated as heat within the planet's interior, contributing to what is known as tidal heating. This internal heating can be significant, especially for planets with eccentric, non-circular orbits, or those involved in strong orbital resonances with other planets, as is the case for the Trappist-1 system. This internal heat can have profound geological consequences, potentially driving volcanism or sustaining subsurface oceans of liquid water, even on worlds that might otherwise be too cold. The tidal forces are not merely slowing the planets down, they are dynamically shaping their internal processes and thermal budgets. Once tidally locked, a planet's day becomes precisely as long as its year. This means it perpetually shows the same face to its star, resulting in a permanent day side bathed in constant starlight and a permanent night side shrouded in eternal darkness. There is no rising or setting of the sun from most points on the surface, except for observers located very near the terminator line, the boundary between day and night, where the star would appear fixed on the horizon. This lack of a diurnal cycle, the familiar alternation of day and night, is one of the most profound consequences of tidal locking, and has enormous implications for planetary climates and the potential evolution of life. The concept of synchronous rotation is often used interchangeably with tidal locking. While a one-to-one synchronous rotation, where one rotation equals one orbit, is the most common and stable outcome of tidal locking for close-in planets, more complex tidal resonances can exist. For instance, a planet might rotate 3 times for every 2 orbits, or 2 times for every 1 orbit, and so on. These are higher-order resonances, but for the Trappist-1 planets, the primary expectation is a one-to-one tidal lock, due to their very close proximity and the long timescales over which these forces act. The resonant chain observed between the Trappist-1 planets themselves, where their orbital periods are mathematically related, e.g., planet B completes 2 orbits for every 3 orbits of planet C, is a separate but related phenomenon. These orbital resonances are a consequence of the planet's mutual gravitational interactions and contribute to the stability of the entire system, preventing them from scattering or colliding over billions of years. Tidal forces from the star play a role in nudging planets into and maintaining these orbital resonances. The stability of tidal locking is a key factor in planetary evolution. Once a planet is tidally locked, it remains in that state for the vast majority of its existence, provided the star itself remains stable. For red dwarfs like Trappist-1, which can live for trillions of years, this means a tidally locked planet will experience billions of years of consistent, non-rotating conditions. This long-term stability is crucial for life, offering an immense window of opportunity for biological processes to take hold and evolve without the disruptive influence of a rotating day-night cycle. However, it also means that any life must adapt to the extreme conditions imposed by the permanent day and night sides. Tidal locking also has implications for a planet's internal structure and the generation of a magnetic field. Earth's magnetic field is generated by the geodynamo, the convection of molten iron in its outer core driven by the planet's rotation. For a tidally locked planet with no rapid rotation, questions arise about how a magnetic field might be sustained. Some theories suggest that strong tidal heating could drive enough convection in the core to maintain a dynamo, even without rapid spin. Other models propose that the planet's core might be offset, or that tidal forces could deform the core in ways that promote convection. A robust magnetic field is critically important for protecting a planet's atmosphere from stellar winds and flares, especially around active red dwarfs. Without it, even a habitable world could have its atmosphere slowly stripped away over long timescales, losing its essential water vapor and other volatile compounds to space. The longevity of a planet's atmosphere, and thus its potential for long-term habitability, is inextricably linked to the presence of a protective magnetic shield. Furthermore, the continuous gravitational flexing due to tidal forces can affect the geological activity of a planet. On Earth, plate tectonics, which are fundamental to regulating our climate and cycling nutrients, are driven by internal heat. Tidal heating, particularly if the planet's orbit is slightly eccentric, not perfectly circular, can provide a significant additional source of internal heat. This extra energy could potentially drive volcanism, maintain convection in the mantle, and even contribute to plate tectonics-like processes on a tidally locked world. Such geological activity would be vital for releasing greenhouse gases into the atmosphere, which are necessary to trap heat from the star, especially for planets at the outer edge of the habitable zone, and for cycling essential elements that life depends on. Without internal activity, a planet could eventually become geologically dead, losing its ability to replenish its atmosphere or cycle nutrients, regardless of its initial conditions. The phenomenon of tidal locking is not unique to the Trappist-1 system. It is expected to be a very common outcome for any exoplanet orbiting close to its star, particularly around the ubiquitous red dwarf stars. Given that red dwarfs are the most numerous stars in our galaxy, and that their habitable zones are necessarily close to the star, it is highly probable that the majority of potentially habitable exoplanets discovered will be tidally locked. This makes the Trappist-1 system an invaluable natural laboratory for studying these prevalent conditions. By observing and modelling the Trappist-1 planets, scientists are gaining crucial insights into the fundamental processes that shape countless worlds across the universe. The implications extend far beyond this single system, informing our search for life across the galactic tapestry. The quiet, relentless tug of gravity orchestrates a permanent celestial tableau where the very concept of a day and night, as we know it, is rendered meaningless, replaced by an enduring duality, a fixed gaze towards a faint red sun. Building upon the fundamental concept of tidal locking, the most profound and immediate consequence for a planet is the complete absence of a traditional day-night cycle. Instead, a tidally locked world is perpetually divided into two distinct hemispheres, a permanent day side eternally facing its star, and a permanent night side forever cast into shadow. This fixed orientation creates extreme environmental gradients across the planet's surface, presenting both significant challenges and fascinating adaptations for climate and any potential life. For the Trappist-1 planets, particularly those residing within the habitable zone, this always day, always night reality defines their very essence, shaping their atmospheres, their water cycles, and the very possibility of sustained biological activity. Understanding these extreme climatic effects is crucial for assessing the true habitability of these distant worlds. The permanent day side of a tidally locked planet would experience perpetual starlight, continuously absorbing energy from its star. For planets close enough to be warm, like Trappist-1e, this could lead to extremely high temperatures. The constant bombardment of stellar radiation would heat the surface relentlessly, potentially causing all surface water to evaporate and creating a thick, steamy atmosphere. On such worlds, if no significant atmosphere exists to redistribute heat, the day side could become a scorching, desiccated wasteland, with surface temperatures so high that rocks might even melt. The sky, perpetually illuminated by the Red Dwarf, would likely appear a deep orange or red, with the star fixed in one position, never moving across the celestial dome. There would be no sunsets, no sunrises, only an unwavering glare. Conversely, the permanent night side would be plunged into eternal darkness and extreme cold. Without any direct stellar illumination, this hemisphere would continuously radiate its heat into the frigid vacuum of space, causing temperatures to plummet dramatically. On an airless, tidally locked world, the night side could reach temperatures approaching absolute zero, cold enough to freeze almost any volatile compound, including gases like carbon dioxide and even nitrogen, onto the surface. This would result in vast glaciers and ice sheets, or even condensed atmospheric gases, forming a desolate, frozen landscape. The only light would come from distant stars, or perhaps a faint glow from its own planet's moon if it had one, or from the dim reflected light of its neighbouring planets, which might appear as large, unmoving disks in the perpetually dark sky. However, the picture becomes far more complex and interesting when considering the presence of a substantial atmosphere. For tidally locked planets within the habitable zone, an atmosphere becomes crucial for moderating these extreme temperature differences. Atmospheric circulation would act as a planetary heat pump, transferring warmth from the scorching day side to the freezing night side. Imagine giant planet-wide wind patterns, constantly moving air from the hot side to the cold side. The most commonly modelled pattern is a large single Hadley cell, where heated air on the day side rises, flows towards the night side at high altitudes, cools and sinks on the night side, and then flows back along the surface towards the day side. This massive air movement would create powerful, constant winds, especially across the Terminator line, potentially exceeding hurricane speeds. These winds would play a vital role in distributing heat and preventing the day side from overheating and the night side from freezing solid. The Terminator line, or twilight zone, emerges as a region of particular interest for habitability. This narrow band between the permanent day and night sides would experience perpetual sunrise or sunset. Here, the star would always hang low on the horizon, bathing the landscape in perpetual twilight. Temperatures in this region could be moderate, perhaps supporting liquid water. The persistent strong winds, however, could make this zone a challenging environment. This twilight belt might be the most hospitable region on a tidally locked planet, a narrow band of warmth and water surrounded by extremes of heat and cold. Some models depict eyeball planets, where a large ocean on the day side might be ringed by a narrow liquid zone that transitions into a vast ice cap on the night side, resembling an eyeball looking at its star. The specific composition and thickness of a tidally locked planet's atmosphere would profoundly influence its climate. A thin atmosphere might not be effective enough at redistributing heat, leaving vast temperature differences between the day and night sides. A thick atmosphere, especially one rich in greenhouse gases like carbon dioxide or water vapour, would be much more efficient at trapping and transporting heat, leading to a more uniform, moderate temperature across the planet. For planets at the outer edge of the habitable zone, like Trappist-1 F or G, a very dense, greenhouse-rich atmosphere might be necessary to raise their overall temperatures above freezing and prevent the entire planet from becoming a snowball. Conversely, for planets closer to the inner edge, like Trappist-1d, too much greenhouse gas could still lead to a runaway greenhouse effect. Cloud formation would also be significantly affected by tidal locking. On the permanent day side, intense evaporation from any surface water could lead to massive, persistent cloud formations, especially near the point directly facing the star. These clouds could help reflect some incoming starlight back into space, providing a cooling effect, but also trap heat as a greenhouse gas. On the night side, extreme cold would likely cause water vapour to condense and freeze out, forming extensive ice clouds or snow. The powerful winds flowing from day to night could also create unique cloud patterns, such as banded cloud structures or a permanent eye wall of clouds surrounding the substellar point. The water cycle on a tidally locked world would be unlike Earth's. Water would evaporate continuously from the dayside's oceans or moist land masses, rising into the atmosphere. The strong global winds would then transport this water vapour towards the night side. As the vapour reaches the colder night side, it would condense and fall as rain or snow, potentially accumulating vast amounts of ice. This could lead to a scenario where the night side becomes a massive ice trap, constantly accumulating water, while the day side becomes increasingly dry over geological timescales. However, if atmospheric circulation is strong enough, or if there are active geological processes, water could be continuously recycled between the two hemispheres or released from the interior. Models vary widely on whether tidally locked worlds would become arid desert worlds on their day sides, or maintain stable hydrological cycles. Challenges for life on tidally locked worlds are considerable. Life would need to adapt to the absence of a day-night cycle, which on Earth drives circadian rhythms and many biological processes. Organisms on the day side would face constant light and heat, while those on the night side would experience endless darkness and cold. Strong, persistent winds would be another significant challenge, potentially eroding landscapes and making it difficult for complex structures to form. Photosynthetic life on the day side would need to adapt to the dim, red light of a red dwarf and its unique spectrum. Life on the night side, if it exists, would likely need to be chemosynthetic, deriving energy from chemical reactions, or reliant on heat and nutrients transported from the day side. Despite these challenges, the long lifespan of red dwarf stars offers an immense timescale for evolutionary adaptation. Over billions, even trillions of years, life could develop novel strategies to cope with the always day, always night reality. Perhaps organisms would migrate between the day and night sides, following seasonal shifts if the planet's orbit is slightly eccentric, or simply adapting to their fixed positions. Subsurface life, insulated from the surface extremes, could also thrive in oceans warmed by tidal heating, as discussed for Trappist-1G. These extreme conditions push the boundaries of our imagination, forcing us to consider truly alien biospheres that might exist on such worlds. The Trappist-1 system provides an unparalleled opportunity to study these tidally locked environments. With multiple planets potentially in the habitable zone, scientists can compare their climates and search for atmospheric biosignatures. The James Webb Space Telescope, with its unparalleled ability to probe exoplanet atmospheres, is poised to reveal whether these planets have atmospheres capable of moderating their extreme day-night differences, and whether those atmospheres harbour any signs of life. The story of Trappist-1, with its fixed gaze towards its faint red sun, is a testament to the universe's boundless creativity and the enduring human quest to find our cosmic kin, even if they live in perpetual twilight or eternal night. Imagine looking up at the sky, not the familiar expanse of brilliant blue that graces Earth, but a canvas painted with hues of deep red, muted orange, or perhaps a perpetual twilight. This is the visual reality that would likely greet an observer standing on the surface of any of the 7 planets orbiting Trappist-1, their faint, cool red dwarf star. The colour of a planet's sky is not arbitrary. It is a direct consequence of the interplay between the star's light and the composition of the planet's atmosphere. On Earth, our sky is famously blue because of a phenomenon called Rayleigh scattering. This process, named after the 19th century British physicist Lord Rayleigh, explains why shorter wavelengths of light, like blue and violet, are scattered more efficiently by the tiny nitrogen and oxygen molecules in our atmosphere than longer wavelengths, such as red and yellow. When sunlight, which contains all colours, enters Earth's atmosphere, the blue light is scattered in all directions, making the sky appear blue. The remaining light, with less blue, reaches our eyes directly from the sun, making the sun appear yellowish white. The fundamental difference for a Trappist-1 planet lies in the nature of its star. Trappist-1 is a red dwarf, which means it is much cooler than our sun. While our sun emits a broad spectrum of light, with a peak in the yellow-green part of the visible spectrum, Trappist-1's light peaks much further into the infrared, or heat, part of the spectrum. In the visible range, it emits significantly more red and orange light compared to blue and green light. If you were to split Trappist-1's light into its component colours, you would find a disproportionate abundance of longer, redder wavelengths, and a comparative scarcity of shorter, bluer wavelengths. This intrinsic colour of the star's light is the primary factor determining the coloration of its planet's skies. Given this dominant red to infrared light, the scattering effects within a Trappist-1 planet's atmosphere would be fundamentally different from Earth's. If the atmosphere was similar in composition and density to Earth's, filled with nitrogen and oxygen, the scattering of the star's light would still occur. However, since there is much less blue light to begin with, there would be very little blue to scatter. Instead, the most abundant wavelengths available for scattering would be red and orange. This would result in a sky that appears predominantly reddish, orange, or even a deep maroon. The exact shade would depend on the density and composition of the atmosphere, as well as the amount of dust or clouds present. A very thick atmosphere might scatter more light, making the sky brighter and more intensely red. A thinner atmosphere might appear dimmer or show a more faded red. The effect of light scattering also influences the apparent colour of the star itself when viewed from the surface. On Earth, the sun appears yellowish white during the day, but takes on reddish hues at sunrise and sunset because its blue light has been scattered away by a longer path through the atmosphere. On a Trappist-1 planet, the star would already be red. As its light passed through the atmosphere, the most scattered wavelengths would still be at the bluer end of its own limited spectrum, which is still primarily red. This might cause the star to appear a slightly deeper red, or even cast a more intense orange glow as its light is attenuated. The visual experience of sunlight would be fundamentally altered, affecting how colours are perceived on the planet's surface. Consider the landscape on a Trappist-1 planet with such a sky. Objects that appear green on Earth because they reflect green light might appear different. If life were to evolve, photosynthetic organisms might develop different pigments to efficiently absorb the dominant red and infrared light from their star, leading to plant life that appears black, deep red, or even metallic in hue to our eyes. Shadows on these worlds would also have a different quality. Instead of the crisp, often bluish-tinged shadows we see on Earth, shadows on a red sky planet would be softer, perhaps with faint reddish or brownish edges, as the ambient light would be so much redder. The entire visual environment would be steeped in a warm, muted palette, vastly different from the vibrant blues and greens of our home world. Beyond the dominant colour, other visual phenomena would be unique to these tidally locked worlds. Since all the Trappist-1 planets are expected to be tidally locked, they would have a permanent day side facing the star and a permanent night side eternally shrouded in darkness. In the permanent day side, the Red Dwarf star would hang motionless in the sky, never rising or setting. It would be a fixed point of light, a constant reddish-orange beacon. This means there would be no familiar cycle of dawn and dusk, no slow progression of shadows across the landscape. The illumination would be constant, leading to unique adaptations for any life forms present, or to stark, unchanging conditions for a barren world. Along the Terminator line, the boundary between day and night, the experience would be one of perpetual twilight. From this narrow zone, the star would always appear on the horizon, either perpetually rising or perpetually setting, never moving higher into the sky. This would create an eternal sunrise or sunset, bathing the landscape in an unending reddish glow, potentially with long dramatic shadows stretching across the terrain. The sky in this region might transition from dark on the night side to bright red on the day side, creating a unique visual gradient. The very concept of time, as marked by the daily cycle of light and dark, would be alien to inhabitants of such a world, replaced by a constant, unchanging illumination. The specific atmospheric composition also plays a crucial role beyond just light scattering. If a Trappist-1 planet has a very thick atmosphere, perhaps denser than Earth's, it could scatter even more light, potentially making the sky appear brighter and more opaque. If the atmosphere contains different gases than Earth's, or significant amounts of aerosols like dust or volcanic ash, these particles could scatter light in different ways, altering the sky colour further. For example, a planet with a substantial amount of sulfur dioxide like Venus might have a yellowish or brownish sky, regardless of the star's colour. If an atmosphere is very thin, the sky might appear dark even during the day, with the red star shining like a bright point in a black void, similar to how the sky appears on the moon during the day, where there is no atmosphere to scatter light. The presence of clouds would also add to the visual complexity. Clouds, composed of water droplets or ice crystals, reflect and absorb light. On a red sky planet, clouds would likely appear in shades of red, orange, or even dark grey, depending on their thickness and altitude. Massive persistent cloud formations might shroud the substellar point on the day side, creating an unending overcast condition. On the night side, if any atmospheric circulation transports water vapour from the day side, ice clouds could form in the perpetual cold, perhaps creating eerie, glowing structures illuminated by the faint light of distant stars or the reflected light of nearby planets. The visual experience of a red sky planet also depends on the planet's internal heat and geological activity. If a planet is volcanically active, plumes of smoke and ash could periodically darken the sky, or volcanic gases could alter atmospheric composition, leading to new colours. The interaction between an atmosphere and any surface liquids, like oceans, would also be unique. Red light penetrates water more deeply than blue light. So, if a Trappist-1 planet has oceans, they might appear darker or have a different range of colours than Earth's blue oceans, perhaps appearing deep red, brown, or even black, depending on their depth and what dissolved substances or life forms they contain. One of the most astonishing features of the Trappist-1 system, second only to the existence of 7 Earth-sized planets, is the incredible proximity of these worlds to each other. Unlike our own solar system, where planets are separated by vast, almost inconceivable distances, the Trappist-1 planets are packed so tightly together that from the surface of one, several of its siblings would appear as prominent, distinct disks in the sky, sometimes many times larger than our own moon. This creates a celestial spectacle unlike anything we experience on Earth, a constantly changing panorama of neighbouring worlds that would profoundly shape the visual landscape and perhaps even the cultural understanding of any inhabitants. The concept of shared skies is not just a poetic notion for Trappist-1, it is a fundamental aspect of its planetary dynamics and visual environment. To truly grasp the compactness of this system, consider the scale. All 7 planets of Trappist-1 orbit their star at distances smaller than the orbit of Mercury around our Sun. Mercury, our innermost planet, averages about 36 million miles, or 58 million kilometres, from the Sun. In contrast, the outermost known planet in the Trappist-1 system, Planet H, orbits its star at an average distance of only about 7.5 million miles, or 12.1 million kilometres. This means the entire Trappist-1 system fits comfortably inside Mercury's orbit. The distances between individual planets are therefore astonishingly small. For example, Trappist-1b and c, the two innermost planets, are separated by only about 1 million miles, or 1.6 million kilometers, at their closest approach. This is less than 5 times the distance between Earth and our Moon. This extreme closeness means that from the surface of any given Trappist-1 planet, its neighbours would appear far larger in the sky than any planet or moon we see from Earth, with the sole exception of our own Moon. Imagine Earth's moon, which has an apparent diameter of about half a degree in our sky. From a Trappist-1 planet, its nearest neighbours could appear 2, 3, or even 5 times larger than our Moon, making them a dominant feature of the celestial landscape. Their precise apparent size would vary depending on their orbital positions relative to the observer, as planets would be closer at some points in their orbits and further away at others. The closest approaches, where planets might swing within 1 million miles or less of each other, would present truly breathtaking views. The visual experience would be profoundly dynamic. As planets orbit their star, they would also be constantly moving relative to each other. This means that an observer on one planet would witness the other planets undergoing phases, much like our Moon, waxing and waning from a thin crescent to a full disk, as different portions of their surfaces are illuminated by the faint red star. These phases would change rapidly, given their short orbital periods. A planet might go from a crescent to a full disk and back again over a matter of days, or even hours, depending on its and the observer's orbital speeds. This would create a celestial clock unlike anything on Earth, where the phases of neighbouring worlds would mark the passage of time. Furthermore, the close proximity would lead to frequent celestial alignments. From the surface of one Trappist-1 planet, an observer would regularly see other planets transit, or pass in front of their parent star. These transits would appear as dark disks slowly moving across the face of the dim red sun. Moreover, mutual transits and eclipses between the planets themselves would be a common occurrence. Imagine one planet casting a shadow onto another, or one planet passing in front of its sibling as seen from a third. Such events would be stunning astronomical phenomena, creating unique and perhaps subtle changes in illumination across the landscape. The frequency and predictability of these events would make them a regular part of the celestial rhythm, potentially incorporated into cultural lore or scientific observation by any intelligent inhabitants. The specific appearance of each neighbouring world would also be distinctive. Depending on its atmospheric composition, surface features, and whether it has clouds or liquid water, each planet would display its unique coloration and patterns. A planet with a thick, steamy atmosphere, like potentially Trappist-1c, might appear as a swirling reddish-brown orb. A potential water world like Trappist-1e might show glints of light reflecting off its oceans, or distinct cloud patterns. A cooler, icier world like Trappist-1,4g could reveal vast white ice caps or subtle variations in its frozen surface. These detailed visual cues would provide constant information about the nature of their sister worlds, turning them from distant points of light into tangible, discernible landscapes. The tidally locked nature of these planets also influences the shared skies experience. Because each planet has a permanent day side and a permanent night side, an observer's view of the other planets would depend on their location on their own world. From the permanent day side, the other planets would appear against a reddish or orange sky, illuminated by the constant glare of Trappist-1. From the permanent night side, they would shine against a dark, star-studded backdrop, illuminated by the direct light of their parent star, reflecting off their surfaces. In the twilight zone, the sky would transition from dark to red, and the other planets might be seen against a perpetually reddish twilight. The movement of the planets in the sky would also be governed by their orbital periods. While they would still orbit and change positions, their movement relative to the observer's fixed point on a tidally locked world might appear different than on a rapidly rotating planet like Earth. The constant presence of large, visible neighbouring worlds would have profound implications for any life or civilizations that might arise on these planets. From a scientific perspective, it would provide an immediate observable laboratory for comparative planetology. Inhabitants would have direct visual access to multiple terrestrial worlds, allowing for detailed observations of their atmospheres, surface features, and even their weather patterns, potentially leading to an early understanding of planetary diversity. This could accelerate scientific and technological development, fostering an innate curiosity about their cosmic neighbourhood. From a cultural and psychological perspective, the shared skies would be incredibly impactful. The other planets would not be distant, abstract points of light, but ever-present companions, a constant reminder of their place in a multi-world system. This might foster a sense of interconnectedness, perhaps even a planetary kinship. The sight of another world hanging large in the sky, possibly undergoing rapid phases, could inspire art, mythology, and religious beliefs centered around the celestial dance. The very concept of world might be fundamentally different, as the idea of a lone planet orbiting its star would seem alien. Their very existence would be intertwined with that of their siblings. The close proximity also means that communication between these worlds, if they were to harbour intelligent life, might be less challenging than interstellar communication across vast light years. Light signals or radio waves would only take seconds or minutes to travel between them, rather than years. This could lead to a system of interconnected civilizations, sharing knowledge and perhaps even travelling between their worlds with relatively less effort than interstellar journeys. However, the physical challenges of space travel, even within such a compact system, would still be immense, requiring advanced technology to overcome gravity and radiation. A planet's atmosphere is a delicate and vital envelope, the very breath of a world. It regulates temperature, distributes heat, shelters the surface from harmful radiation, and provides the raw materials for life. However, this atmosphere is not a static entity. It is constantly interacting with the forces of its star and the harsh vacuum of space. For planets orbiting close to active stars like the 7 worlds of Trappist-1, the presence or absence of a planetary magnetic field becomes a crucial determinant of their long-term habitability. A magnetic field acts as a shield, deflecting the relentless onslaught of stellar winds and high-energy particles that would otherwise strip away a planet's atmosphere, turning potentially habitable worlds into barren, lifeless rocks. Understanding the magnetic fields, or lack thereof, around the Trappist-1 planets is therefore fundamental to assessing their true potential for harbouring life. A planetary magnetic field is generated by a process known as the dynamo effect. Deep within a planet, if it possesses a molten, electrically conducting core, and if that core is undergoing convection, the rising and sinking of hot and cool material, and rotation, a self-sustaining magnetic field can be created. Earth's magnetic field is a prime example. Our planet has a molten iron core, and the combination of its rotation and the convection within the core creates electric currents that generate a powerful magnetic field. This field extends far into space, forming a region called the magnetosphere, which deflects the solar wind, a constant stream of charged particles emitted by the sun. Without this magnetic shield, Earth's atmosphere would have been gradually eroded over billions of years, potentially leading to a fate similar to Mars, which lost most of its atmosphere and surface water. The strength of a planet's magnetic field depends on several factors: the size and composition of its core, the rate of its rotation, and the intensity of convection within the core. A larger core with more molten material can generate a stronger field. Faster rotation also tends to enhance the dynamo effect. However, the most critical factor is often the presence and intensity of convection. If the core is not actively convecting, even a rapidly rotating planet might have a weak magnetic field. The source of this convection can be either heat from the planet's formation, or, crucially for tidally locked planets, tidal heating. Tidal heating, as discussed in previous chapters, is the internal heat generated by the gravitational flexing of a planet due to its star's tidal forces. For the Trappist-1 planets, the question of magnetic fields is particularly complex. They are all expected to be tidally locked, meaning they do not have a rapid, Earth-like rotation. This raises the question of whether they can sustain a dynamo effect. If a planet is not rotating, it might seem impossible to generate a magnetic field. However, tidal heating could provide an alternative energy source for driving core convection. The intense gravitational tugs from Trappist-1 and the other planets, particularly in their resonant orbits, could cause significant internal heating, potentially maintaining a molten, convecting core, even without rapid rotation. However, the effectiveness of tidal heating in generating a magnetic field is still a subject of scientific debate. Some models suggest that it can be sufficient to drive a dynamo, especially if the planet has an eccentric, non-circular orbit, leading to more intense tidal forces. Other models are less optimistic, suggesting that the convection might be different from that driven by rotation, perhaps less organised, and therefore less efficient at generating a strong global magnetic field. The exact strength and configuration of any magnetic fields around the Trappist-1 planets are currently unknown. The nature of Trappist-1 itself, as an active red dwarf star, adds another layer of complexity. Red dwarfs, while much cooler than our Sun, are often prone to powerful stellar flares and bursts of high-energy radiation, especially early in their lives. These flares can be many times more intense than solar flares, and their frequent occurrence poses a significant threat to the atmospheres of any orbiting planets. A strong magnetic field is crucial for deflecting these energetic particles and preventing atmospheric erosion. Without a magnetic shield, a planet's atmosphere could be gradually stripped away over billions of years, losing its water vapor and other volatile compounds to space. The proximity of the Trappist-1 planets to their star exacerbates this problem. Because they orbit so closely, they are subjected to a much higher flux of stellar radiation than Earth. This means that even if a Trappist-1 planet has a magnetic field, it might need to be exceptionally strong to effectively shield its atmosphere. The balance between the planet's magnetic field strength and the intensity of the stellar wind is a critical factor in determining its long-term habitability. A weak magnetic field might offer little protection, even if the planet is otherwise within the habitable zone. The potential for a magnetic field also depends on a planet's internal structure and composition. To generate a dynamo, a planet needs a substantial, electrically conducting core. The size and composition of the core, the presence of a solid inner core, and the efficiency of heat transfer within the core all influence the strength of the magnetic field. The densities of the Trappist-1 planets, derived from transit timing variations, suggest that they are primarily rocky, with compositions similar to Earth. This means they likely have iron-rich cores. However, the presence of water or other volatile compounds, particularly in the outer layers, could affect the core's dynamics and its ability to generate a magnetic field. The study of exoplanet magnetic fields is an extremely challenging endeavour. We cannot directly measure the magnetic fields of planets orbiting distant stars. Instead, scientists rely on indirect methods and theoretical models. One approach is to look for auroras, similar to Earth's northern and southern lights, which are created when charged particles from the solar wind interact with a planet's magnetic field. Detecting auroras on an exoplanet would be a strong indication of a magnetic field. However, auroras are faint and difficult to observe, especially around red dwarf stars, whose light is much dimmer than our Sun. Another approach is to study the interaction between a planet's atmosphere and the stellar wind. If a planet has a strong magnetic field, it will create a bow shock, a boundary where the stellar wind is deflected around the planet. Observing this bow shock, or the absence of it, could provide clues about the presence and strength of a magnetic field. However, these observations are also extremely challenging, requiring very sensitive instruments and long observation times. Theoretical models play a crucial role in understanding the potential for magnetic fields on exoplanets. Scientists develop computer simulations of planetary interiors, modelling the core's dynamics and the generation of magnetic fields under different conditions. These models take into account factors like the planet's size, composition, rotation rate, or tidal locking, and the intensity of tidal heating. By comparing the results of these models with observations, scientists can refine their understanding of the conditions necessary for a planet to generate a magnetic field. For the Trappist-1 planets, the question of magnetic fields remains one of the most pressing unknowns. The James Webb Space Telescope, with its ability to probe exoplanet atmospheres, might provide indirect clues. If a planet's atmosphere shows signs of being eroded by stellar winds, it could indicate a weak or absent magnetic field. Conversely, a stable, thick atmosphere, particularly around a planet close to the star, might suggest the presence of a protective magnetic shield. Ultimately, a deeper understanding of the magnetic fields around the Trappist-1 planets will require future missions and advanced technologies capable of more direct observations. The presence or absence of these invisible shields will profoundly influence our assessment of these worlds' potential for life, reminding us that habitability is not just about distance from a star, but also about the complex interplay of internal and external forces that shape a planet's long-term destiny. The search for life beyond Earth is one of humanity's most profound and enduring quests. While the discovery of exoplanets has shown that planets are abundant throughout the galaxy, determining whether any of these distant worlds are truly habitable or even inhabited requires a deeper understanding of their atmospheres. A planet's atmosphere is its lifeblood, regulating temperature, distributing heat, and providing the chemical ingredients for life. It is the interface between the planet's surface and the harsh environment of space, a delicate and dynamic envelope that holds the key to unlocking the secrets of habitability. For the Trappist-1 planets, the quest to characterize their atmospheres is particularly urgent, as several of these worlds reside within the star's habitable zone, making them prime targets in the search for extraterrestrial life. However, studying the atmospheres of exoplanets is an incredibly challenging endeavour. These planets are incredibly distant and faint, their light often overwhelmed by the brilliance of their parent stars. To overcome these obstacles, astronomers have developed ingenious techniques, the most powerful of which is transmission spectroscopy. This method, often described as atmosphere hunting, allows scientists to probe the chemical composition of a planet's atmosphere by analysing the starlight that passes through it. The principle behind transmission spectroscopy is elegant. When a planet transits, or passes in front of, its star, a tiny fraction of the star's light travels through the planet's atmosphere before reaching our telescopes. Different gases in the atmosphere absorb specific wavelengths, colours, of light. By carefully measuring the small changes in the star's spectrum during a transit, astronomers can identify the presence and abundance of these gases. Imagine shining a white light through a prism. The prism splits the light into its component colours, creating a rainbow. This is a spectrum. Each element and molecule has a unique spectral fingerprint, a pattern of dark lines or bands where it absorbs light. If you shine white light through a gas and then through a prism, the resulting spectrum will have dark lines at the wavelengths where that gas absorbed the light. By analysing these dark lines, you can identify the gas and measure its concentration. Transmission spectroscopy applies this same principle to exoplanet atmospheres. The starlight acts as the white light. The planet's atmosphere acts as the gas, and our telescopes, equipped with spectrographs, act as the prism, splitting the starlight into its component colours and revealing the atmospheric fingerprints. The amount of starlight that passes through a planet's atmosphere during a transit is incredibly small, often less than 1% of the total starlight. This means that detecting the subtle changes in the spectrum requires extremely sensitive instruments and long observation times. The signal is strongest when the planet is large relative to its star, and when the planet's atmosphere is thick and contains abundant gases that absorb light strongly. Red dwarf stars like Trappist-1 are particularly well suited for this technique because they are much smaller and dimmer than our Sun. A planet of a given size blocks a larger fraction of light from a red dwarf, making the transit signal more pronounced. This is one of the reasons why the Trappist-1 system is such a prime target for atmospheric studies. The information gleaned from transmission spectroscopy is invaluable. By identifying the gases present in an exoplanet's atmosphere, scientists can begin to understand its temperature, pressure, and overall chemical environment. The detection of the water vapour, for example, is a crucial indicator of potential habitability. Water is essential for life as we know it, and its presence in an atmosphere suggests that liquid water might exist on the planet's surface. Other important gases include carbon dioxide, a key greenhouse gas that helps regulate temperature, and methane, which, while it can be produced by geological processes, is also a potential biosignature, a sign of life. The search for biosignatures, gases that could indicate the presence of life, is a primary goal of exoplanet atmospheric studies. Oxygen is perhaps the most famous biosignature. On Earth, oxygen is produced primarily by photosynthesis, and its presence in our atmosphere is a direct result of biological activity. However, oxygen can also be produced by non-biological processes, such as the breakdown of water molecules by ultraviolet radiation. Therefore, the detection of oxygen alone is not a definitive sign of life. A more compelling biosignature is the simultaneous detection of oxygen and methane. These two gases react with each other and would not persist in an atmosphere unless they were constantly replenished by a source, which on Earth is primarily biological. However, the interpretation of biosignatures around red dwarfs can be complex. The unique light spectrum of a red dwarf, with its abundance of infrared radiation, might favour different types of photosynthesis than those on Earth. Furthermore, the active nature of red dwarfs, with their frequent flares, could potentially produce or destroy certain atmospheric gases in ways that might mimic or obscure biosignatures. For example, stellar flares could break down water molecules, producing oxygen, or they could destroy methane. Therefore, any potential detection of biosignatures would require extensive follow-up observations and careful analysis to rule out false positives. The James Webb Space Telescope, JWST, is a revolutionary instrument specifically designed for exoplanet atmospheric studies. Its large mirror, its ability to observe in the infrared, and its advanced spectrographs make it uniquely suited to probe the atmospheres of small distant planets like those in the Trappist-1 system. Webb can observe at wavelengths where many important atmospheric gases, including water vapour, carbon dioxide, methane and ozone, have strong absorption features. Its sensitivity and resolution are far superior to any previous telescope, allowing it to detect even trace amounts of these gases in exoplanet atmospheres. The Trappist-1 planets are among the first targets for Webb's atmospheric investigations. The goal is to determine whether these planets have atmospheres, what they are composed of, and whether any of them show signs of habitability or even life. Webb's observations will focus on the planets that are most likely to have liquid water on their surfaces, particularly Trappist-1d, E, F, and G. The initial observations will aim to determine the basic atmospheric properties, such as temperature, pressure, and the presence of major gases like water vapour and carbon dioxide. If these planets have detectable atmospheres, Webb will then search for more subtle features, including potential biosignatures. The challenges of studying the atmospheres of the Trappist-1 planets are immense. These planets are small and faint, and their atmospheres are likely to be thin and tenuous. The transits are also relatively short, lasting only a few hours. This means that Webb must observe these planets for extended periods, collecting as much light as possible to detect the faint atmospheric signals. The data analysis is also complex, requiring sophisticated models to separate the atmospheric signals from the noise and to account for the effects of the star's light and the instrument's characteristics. The results of Webb's atmospheric studies of the Trappist-1 planets will have profound implications for our understanding of exoplanet habitability and the search for life beyond Earth. If Webb detects stable, moderate atmospheres with evidence of water vapour and other key gases, it would greatly increase our confidence that these planets could potentially support life. The detection of biosignatures, while a long shot, would be a transformative discovery, providing the first concrete evidence that we are not alone in the universe. Even if Webb does not find biosignatures, simply characterizing the atmospheres of these planets will provide invaluable data for testing and refining models of planetary climate and atmospheric evolution. The quest to understand the atmospheres of the Trappist-1 planets is a journey into the very heart of the search for life, a scientific endeavour driven by both rigorous data and an enduring human curiosity about our place in the cosmos. Water is often considered the elixir of life, a fundamental requirement for all known biological processes on Earth. Its unique properties, such as its ability to dissolve a wide range of substances, its high heat capacity, and its existence in liquid form over a broad temperature range, make it an indispensable solvent and medium for the complex chemical reactions that underpin living organisms. Without liquid water, the intricate machinery of cells simply cannot function. Therefore, in the grand cosmic search for life beyond Earth, the presence of liquid water on a planetary surface or within its interior is often the primary criterion that astronomers and astrobiologists look for. The Trappist-1 system, with its 7 Earth-sized planets, has emerged as a beacon of hope precisely because of the strong evidence and compelling theories suggesting the widespread presence of water throughout its planetary family, albeit in various states and locations. The primary evidence for water in the Trappist-1 system comes from the careful measurements of the planet's densities. When astronomers discovered these worlds using the transit method, they were able to precisely measure their sizes by observing how much starlight each planet blocked during its passage in front of the star. Simultaneously, by meticulously tracking the tiny variations in the timing of each planet's transit, caused by the gravitational tugs they exert on each other, scientists were able to determine their masses. With both the mass and the radius, from which volume can be calculated, known for each planet, astronomers can then calculate its average density. Density provides a crucial clue about a planet's bulk composition. For example, a rocky planet like Earth has a higher density than an icy planet or a gas giant. The densities of the Trappist-1 planets are particularly revealing. While all 7 planets are roughly Earth-sized and appear to be primarily rocky, several of them, particularly the outer ones, have densities that are significantly lower than what would be expected for a purely rocky or iron-rich body like Earth. This lower density strongly suggests the presence of a substantial amount of lighter, volatile materials in their composition, with water being the most likely candidate. For instance, Trappist-1F and G, which are both within the habitable zone, have densities consistent with having a significant fraction of their mass composed of water, potentially 5% or more. To put this in perspective, Earth is only about 0.02% water by mass. If these planets truly contain such a large proportion of water, they could be considered true water worlds, possessing far more water than our own planet. This abundance of water is a crucial piece of the puzzle in assessing their habitability. The distribution and state of water within the Trappist-1 system are thought to vary significantly from planet to planet, largely determined by their distance from the faint red star. For the innermost planets, Trappist-1b and Trappist-1c, their extreme proximity to the star means they receive a colossal amount of stellar radiation. While Trappist-1 is a cool red dwarf, emitting primarily infrared light, the sheer intensity of this heat at such close range would have profound effects. Scientists theorize that any surface water these planets might have possessed during their formation or early history would have long since boiled away. This process is known as a runaway greenhouse effect, where evaporating water vapor, a powerful greenhouse gas, traps more heat, leading to further evaporation until all surface water is lost to the atmosphere and eventually stripped away into space by the star's powerful winds and ultraviolet radiation. Therefore, while these planets may have formed with water, their current surfaces are likely baked, barren, and devoid of stable liquid water. Any remaining water would likely exist as highly compressed steam in a super-dense atmosphere, or perhaps locked away deep within the planet's mantle in mineral form, but not in a state conducive to life. The real excitement regarding water lies with the planets located within Trappist-1's habitable zone, Trappist-1d, E, F, and G. These are the worlds where temperatures could potentially allow for liquid water to exist on their surfaces or in subsurface reservoirs. Trappist-1d, being at the inner edge of the habitable zone, is a borderline case. It receives a stellar flux comparable to Earth's. If it has a moderate atmosphere, it could potentially maintain liquid water on its surface. However, a slightly thicker atmosphere, or one with too many greenhouse gases, could push it into a runaway greenhouse state similar to its inner siblings losing its surface water. Its density is slightly lower than Earth's, which also hints at a significant water content, possibly up to 5% by mass. If water is present, it might exist as shallow oceans, or perhaps primarily as ice with only localized melting in warmer regions, or during specific orbital configurations. The precise amount of water and the efficiency of atmospheric heat redistribution would determine its watery fate. Trappist-1e is considered one of the most promising candidates for liquid water. It receives approximately 94% of Earth's stellar flux, placing it firmly within the habitable zone. Its density is very similar to Earth's, suggesting a rocky composition, but with the potential for abundant surface water. Scientists envision Trappist-1e as a potential water world with vast global oceans. These oceans, if they exist, would be liquid due to a moderate greenhouse effect from its atmosphere. The tidally locked nature of Trappist-1e would create a permanent dayside and nightside. If it has extensive oceans, powerful ocean currents could help redistribute heat from the perpetually warmed dayside to the cooler nightside, preventing it from freezing solid. This scenario would make it a prime candidate for marine life, with diverse ecosystems thriving within its liquid embrace. Trappist-1e, situated further out in the habitable zone, receives less stellar energy than Planet E, making it a cooler world. Its significantly lower density, suggesting a water content of 5% or more by mass, makes it a very strong candidate for possessing substantial water, likely in the form of a thick ice mantle, but with the strong possibility of a deep subsurface ocean. This subsurface ocean would be maintained in a liquid state by internal heat sources, primarily tidal heating. As Trappist-1f orbits its star and interacts gravitationally with its neighbouring planets, in their intricate orbital resonance, the planet is constantly stretched and squeezed. This internal flexing generates friction and heat, warming the interior sufficiently to melt ice deep below the surface, creating a vast liquid realm, protected from the cold surface and the harsh stellar flares. Such subsurface oceans, akin to those thought to exist on Jupiter's moon, Europa or Saturn's moon, Enceladus in our solar system, could potentially host chemosynthetic life, independent of sunlight. Trappist-1g, the sixth planet, is located even further out, towards the very cold edge of the habitable zone. It receives only about 38% of Earth's stellar flux, meaning its surface would likely be entirely frozen. However, its density is the lowest among the three innermost habitable zone planets, suggesting an even higher proportion of water, possibly 10% or more by mass. This implies Trappist-1g is almost certainly a global ice world, with a thick crust of ice blanketing its entire surface. Similar to Planet F, the most compelling theory for liquid water on Trappist-1g involves a deep subsurface ocean, warmed by powerful tidal heating from its star and orbital resonances with its close-knit siblings. If such an ocean exists, it would represent a vast, dark, and potentially active environment where life could thrive, sustained by geothermal energy emanating from the planet's interior. Finally, Trappist-1h, the outermost known planet, is far beyond the habitable zone, receiving very little stellar energy. Its surface would be extremely cold, likely an entirely frozen world with its water locked up in a thick ice mantle. While its density suggests a high water content, the tidal heating acting upon it is likely much weaker due to its greater distance from the star. Therefore, the possibility of a widespread liquid subsurface ocean is considered much lower than for planets F and G, though perhaps some localized liquid pockets might exist deep within its icy interior due to remnant heat or localized geological activity. It essentially marks the boundary beyond which water is predominantly in its solid frozen state. The origin of such abundant water on these planets is a subject of ongoing research and modelling. One theory suggests that the planets formed further out in the Trappist-1 system, beyond the snow line, the distance from a star where it is cold enough for volatile compounds like water to condense into solid ice. In this scenario, the planets would have accreted significant amounts of water ice during their formation. They would then have migrated inwards to their current close-in orbits, bringing their water reservoirs with them. Another possibility is that water was delivered to these planets early in their history through collisions with icy comets or asteroids. Regardless of the exact mechanism, the evidence points to a system rich in water, a crucial factor for the potential emergence of life. The primary tool for directly detecting water on these distant worlds is the James Webb Space Telescope. While planetary densities provide strong indirect evidence for water, Webb's advanced instruments are designed to look for water vapour in the planet's atmospheres. During a transit, as the star's light passes through the planet's atmosphere, molecules of water vapour would absorb specific wavelengths of that light, leaving a distinct spectral fingerprint. By detecting these fingerprints, astronomers can confirm the presence of water vapour and estimate its abundance. Initial observations with Webb have already begun this process, and while definitive results require more data, the potential for directly confirming atmospheric water vapour, particularly on planets D, E, F, and G, is immense. Confirming the presence of liquid oceans, especially subsurface ones, is far more challenging. For surface oceans, future instruments might be able to detect glints of reflected starlight, or observe variations in temperature that are consistent with large bodies of water. For subsurface oceans, the challenge is greater. Scientists would look for indirect signs, such as evidence of cryovolcanism, ice volcanoes, on the surface, or specific atmospheric gases that might be vented from a subsurface ocean. Precisely measuring the tidal heating within these planets and how it might deform their shape could also provide clues about internal liquid layers. The theories and evidence surrounding water on the Trappist-1 planets paint a picture of a truly remarkable system. From the potentially desiccated inner worlds to the potentially ocean-covered or ice-mantled outer worlds, water, in its various forms, appears to be a ubiquitous component of this planetary family. This abundance of water, combined with the fact that several planets reside within the habitable zone, makes Trappist-1 an unprecedented target in the search for life. It is a system that reminds us that the universe might be a wetter place than previously imagined, with liquid water potentially existing in a myriad of forms and locations awaiting discovery. For centuries, the question of whether life exists beyond Earth was relegated to the realm of philosophical debate and imaginative storytelling. It was a grand idea, a tantalizing possibility, but one without scientific footing. However, in the past few decades, our understanding of the cosmos has undergone a profound revolution. The discovery of thousands of planets orbiting distant stars, known as exoplanets, has transformed the question from pure speculation into a vibrant and active field of scientific inquiry. We now understand that planets are not rare exceptions but a common feature of our galaxy, vastly increasing the cosmic real estate where life might potentially arise. This growing body of knowledge makes a compelling case for the general possibility of life existing elsewhere in the universe, suggesting that our Earth might not be a unique biological anomaly, but one example among countless possibilities. The foundation of life as we know it, Earth life, relies on a set of fundamental ingredients and conditions. These ingredients include a stable source of energy, typically a star, a solvent, universally water, and a suite of chemical building blocks, primarily carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Beyond these chemical components, life also requires a relatively stable environment over long timescales, allowing complex biological processes to unfold and evolution to proceed. These ingredients, far from being unique to Earth, are abundant throughout the cosmos. Carbon, the backbone of all known organic molecules, is a remarkably versatile element, capable of forming long, complex chains and rings that are essential for the intricate structures of proteins, DNA, and other biological compounds. It is created in the cores of stars and dispersed throughout the galaxy in stellar explosions, making it readily available in the vast clouds of gas and dust from which new stars and planets form. Hydrogen and oxygen, the constituents of water, are among the most abundant elements in the universe. Hydrogen was forged in the Big Bang itself, and oxygen is produced in massive stars. Nitrogen, phosphorus, and sulfur are also common, formed through various stellar processes and distributed across galactic space. The very atoms that compose life on Earth are universal, suggesting that the basic chemistry for life is not an exotic local phenomenon, but a widespread cosmic potential. The discovery of exoplanets has fundamentally altered our perspective on the prevalence of suitable environments for life. Before the 1990s, we only knew of the 8 planets in our own solar system. Now, thanks to observatories like the Kepler Space Telescope and follow-up missions, we have confirmed the existence of over 5,000 exoplanets, with thousands more awaiting confirmation. What is even more remarkable is that these discoveries have shown that planetary systems are incredibly diverse. We have found gas giants orbiting incredibly close to their stars, super-Earths, much larger than our planet, and even mini-Neptunes that have no direct analogue in our solar system. Crucially, among these thousands of discoveries, many are Earth-sized or slightly larger, and a significant number are located within their star's habitable zone. The habitable zone, sometimes referred to as the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. It's not too hot for water to evaporate into space, and not too cold for it to perpetually freeze. The size and location of a star's habitable zone depend on the star's type and luminosity. Hotter, more massive stars have wider habitable zones located further out, while cooler, dimmer stars, like red dwarfs, have narrower habitable zones located much closer in. The fact that astronomers are finding Earth-sized planets within the habitable zones of various types of stars, including red dwarfs like Trappist-1, suggests that the conditions for liquid water might be far more common than previously imagined. The sheer number of stars in the observable universe is staggering. Our Milky Way galaxy alone contains an estimated 100 billion to 400 billion stars, and there are likely trillions of galaxies in the observable universe. This translates to an astronomical number of potential planets. Even if only a tiny fraction of these planets are in the habitable zone and possess the right conditions, the sheer statistical probability suggests that there could be billions of potentially habitable worlds in our galaxy alone, and countless more across the universe. This numbers game forms a powerful argument for the widespread occurrence of life. Furthermore, our understanding of life as we know it has expanded dramatically through the study of extremophiles on Earth. These are organisms that thrive in environments once thought to be utterly hostile to life, such as superheated volcanic vents at the bottom of the ocean, highly acidic waters, intensely salty brines, deep underground rocks, or even radiation-filled environments. The existence of extremophils demonstrates that life can be remarkably resilient and adaptable, pushing the boundaries of what we previously considered habitable. This broadens the definition of habitability for exoplanets, suggesting that life might not require conditions identical to Earth's surface, but could exist in a much wider range of planetary environments, including subsurface oceans on icy worlds or deep within a planet's crust. For example, the strong evidence for subsurface oceans on Trappist-1 and G, potentially warmed by tidal heating, opens up a whole new realm of possibilities for life existing in dark, watery environments, independent of sunlight. However, the question of a life beyond Earth is not merely about finding suitable planets. It also involves the colossal step of abiogenesis, the process by which non-living matter gives rise to life. How did the first life forms arise from a primordial soup of chemicals on early Earth? This remains one of the deepest mysteries in science. While we have made significant progress in understanding the chemical reactions that could have led to the building blocks of life, the exact transition from chemistry to biology is still unknown. If abiogenesis is a relatively common and inevitable outcome when the right conditions persist for long enough, then life might indeed be widespread. If it is an exceedingly rare and improbable event, then Earth life might be an anomaly. The answer to this question profoundly impacts the probability of life elsewhere. The longevity of stars, particularly red dwarfs, also plays a crucial role. Our Sun has a lifespan of about 10 billion years, and life on Earth took roughly 3.8 billion years to emerge and evolve to complexity. Red dwarf stars like Trappist-1 can live for trillions of years. This offers an almost unimaginable amount of time for life to originate, adapt, and evolve on their planets. Even if the process of abiogenesis is slow or requires multiple attempts, the extended stable period provided by a red dwarf offers ample opportunity for life to take hold and potentially develop into complex, even intelligent forms. This vastly increases the window of opportunity for life compared to planets around shorter-lived, more massive stars. The search for life beyond Earth currently employs various strategies. Passive listening efforts, such as the Search for Extraterrestrial Intelligence, or SETI, use radio telescopes to scan the skies for artificial signals, hoping to detect techno-signatures, evidence of technology developed by an alien civilization. More recently, the focus has expanded to searching for biosignatures in exoplanet atmospheres. As discussed in the previous chapter, telescopes like the James Webb Space Telescope are designed to look for specific gases in the atmospheres of potentially habitable worlds, such as oxygen, methane, or ozone, which could be indicative of biological activity. The detection of such gases would be a monumental step, providing indirect but powerful evidence for life. The philosophical implications of discovering life, especially intelligent life, are immense. It would fundamentally change our understanding of humanity's place in the universe. Are we unique, or are we part of a vast cosmic tapestry of living worlds? The famous Fermi paradox, for example, asks, if life is common, and given the vastness and age of the universe, why have we not yet detected any signs of intelligent alien civilizations? This paradox has led to various proposed solutions, including the Great Filter hypothesis, which suggests that there might be some enormous barrier or series of barriers that life must overcome to reach a technologically advanced stage, and that perhaps we are either extremely rare or we are yet to encounter this filter ourselves. The Trappist-1 system is particularly interesting in this context, as it offers multiple candidates for life in a single compact system, potentially providing a density of life that could make detection easier.